The following message is best viewed on an oscilloscope.
Welcome to our session on detectors for future facilities, R&D and novel techniques. And today is the third session. We hear about calorimetry, new silicon gas detectors, and also then for space and ultra-low background experiments, some new technologies. I welcome you all to this virtual event. Unfortunately, we can't be in Prague today. So the speakers, each speaker you have 15 minutes. It's 12 minutes of talk and 3 minutes of discussions. I kindly ask all of you to mute while you're not presenting, and then also wait for questions until the end of the presentation. So for the questions, we will use the raise hand feature. So you just mark it in Zoom, and then I will call you on. And also we have the Mattermost channel. So if you have here any points, questions for the discussion, and which we will also monitor. And so let's have a fruitful discussion. We're looking forward to many presentations this morning. And I would like to call Narei, Lorenzo, Martinez for the first presentation on the development of the ATLAS liquid argon calorimeter readout electronic.
Yes, hello.
Good morning.
Good morning. Yes, so I'm sharing the slides. Okay, can you see them?
Yes, go ahead.
Perfect. So I'm starting. So good morning, everyone. I'm going to talk about the development of the liquid argon electronics for ATLAS HL-LHC development. So just to remind you, this HL-LHC program, so it's starting around 2027 after 2 years of shutdown. And the goal is to go to about 5 times more luminosity that we have currently, and with a very large value of about 200. And there's so at the end, the goal is to reach at ultimately 4,000 inverse Webb-Burn. So why we are upgrading the calorimeter system? So first, we are not upgrading the detector themselves, but just the electronic part. And we are upgrading because there is an incompatibility with the future ATLAS trigger scheme, and also because the electronic is not qualified for such high luminosity and pileup. And also we want to benefit from technological progress we have currently. So the goal is really to maintain and then even enhance the physics reach during HL-LHC. So on the next slide, so just to remind also what I'm talking about when I say liquid argon calorimeters. So there are 4 subdetectors when I say that. So there is the electromagnetic end cap and barrel. And also you have the hadronic end cap here, and the forward part also, which are made of liquid argon. If I just zoom on the barrel part, you see some electrode with accordion shape. And between this electrode, you have absorbers made of lead, and everything is filled with liquid argon. So when a charged particle cross, you get an ionizing signal, which has this typical triangular shape. And the goal, in fact, of this electronic chain is to preamplify shape and digitize this ionization pulse. So you get at the end this bipolar pulse. So this has to be done for 200,000 cells and from 50 MeV to 3 TeV with at the most 1% constant term. So this is something quite challenging to do. And this has to be done for the next upgrade. So I just put here a schematic of the full electronic check. So on the bottom part, you have the what is being currently upgraded. This is the trigger path. And this you can have more detail on the Pavel talk from yesterday. And on the top part is what I'm going to talk about. You have the on detector part on the left, which is made of front-end board, which make the full preamplification, shaping, etc. And you have and you will need about 1,500 boards for that. You have the calibration system with about 130 boards. And also you have the hop detector part, which is made of a large signal processor, which compute energy, etc. And you need also about 400 boards. And a new system, which is a timing system, you need about 20 boards. So it makes a lot of work to be installed in the next years. So I start with the calibration system on slide 5. So the goal of this system is to inject an exponential pulse of non-amplitude and to probe what is the electronic response on the detector cell. So it's a simple system where you have, as you can see on the top diagram, you have a DAC that's sending the command, and then you have two transistors that are switching. And that's produce a pulse that is then put in shape with the RL system, which is on the bottom. So the system is quite simple, but the goal is to get a very good non-linearity of the level 1 per mil, and also an uniformity across all channels of about 0.25%. And this for a 16-bit dynamic range. And also we need this system to be, of course, radiation tolerant up to 1.8 kilogram. So at the moment, we are already at the second version of prototyping. We have an ASIC that contains the DAC and the transistor, so the switching part, in XFAB edge voltage shift CMOS technology, 180 nanometer. And we have received the board and the chip in January 2020, and from them we are testing them. The tests in laboratory are quite good because they show an excellent linearity of the DAC 10 bits. So the one going to 5 milliamperes at the level of 0.05%. And the switching part also is quite good at the level of 1 per mil. But the 13-bit DAC and the 16-bit DAC, so the part that allows to go to the 300 milliamperes, has a large INL, which is attributed to bit mismatch and needs to be improved in the next version. So you can see also on the right the picture of the testing board, and the ASIC we are testing is on the middle. So now, just on the top right, you can see the switch non-linearity that I just talked about, and then you can see the good performance. And we also made extensive tests under TID radiation up to 10 kilogray. And we have shown during this test that the high frequency part, so the switching part, and the current mirror, so the part that allows to go from 40 milliamperes to 300 milliamperes, is stable under irradiation. But it's not the case of the first part of the DAC from 0 to 40 milliamperes, because it's already degraded after 0.5 kilogray. So this is really something that prevent us to use this technology, and we need to go for another one, which is TSMC 130 nanometer for the next version. You can see the result of the irradiation on the bottom with the VT drift of one of the transistor as a function of the dose, and you see it's the shift is really small. So this is why we can qualify the switching part for irradiation. And on the right, you see the DAC, which is not performing well when you start to irradiate more and more. So then next step is to submit two ASICs, one with the XFAB technology for the part that works under radiation, and another in TSMC, as I've just said, with also improved linearities functions. And also we are working on the first prototype of the 32 channel calibration board. And you can see on the right a schematic of what we are already working on the communication between LPGBT, fast common decoder, the monitoring, etc. So now if I go to the front end part, you see that the goal is to perform the preamplification, the splitting in 2-gain scale, the low and an high gain. And you also need a CRRC2 shaping, and at the end also a summing of channels for the L0 trigger. And again, also the radiation tolerance at the same level. So there are two types of ASIC that are in the test. You have the low rock V2, which are both, in fact, in CMOS TSMC 130 nanometer technology. So the first ASIC, you can see a picture on the top right. The ASIC is on the middle, and the dies have been received this January. And for the moment, all properties are within specification, except maybe for a low gain over high gain ratio, which is a bit over. But then the next step is just a proton irradiation to fully qualify this. And the second chip that is being tested is a Alphi V1. So for this is less advanced development, because only 2 boards with the first version of the ASIC are available and starting just now the test. And you also have a design on the new version, which is the V1B, with all features that will be ready by this summer and then tested only by the end of the year or next year. So if you go to the next slide, you see the digitization part. So now after you have the analog signal, and this allows to really digitize at 40 megahertz and to get the 14-bit dynamic range with a better than 11-bit precision. So there are 2 types of ASIC. So the first one is a really full custom ASIC in this TSMC 65 nanometers. It is made, if you see the bottom left plot, it's made of dynamic range enhancer and 4 multiplying DAC channels. And then you have a pipeline, a 12-bit pipeline successive register. And then you have the digital data processing unit at the end that makes the ADC code and the output to the LPGBT. So the study, there are a lot of study of the performances, and one example is the resolution of the LAR pulse, like you can see on the middle plot. And you can see that this resolution, in fact, is within spec in almost full dynamic range. And you're also the property, we have checked the crosstalk, which is very small. So the next step, again, proton irradiation to fully test this. And the other thing we are testing at the moment is to reuse an ADC IP core that has been already developed by Adisto S3 company for the CMS electronic calorimeter in TSMC also 65. And this is already the second version, which has been improved, for example, by better splitting the analog and digital part, as you can see on the right bottom plot. So once you have all these ingredients, you have also the front-end board that contains everything. You have, as you can see on this diagram, you need the preamp shapers, which are the low rock. Then you have the ADC, which is the Coluta, and then you have the LPGBT, which is the LPGBT V1, and then of course the VTRX. So this is the first slice board that we are testing with only 8 of each, and we start the test on the fall. And the full prototype with the 128 channels is start to be prepared, and we will have this for 2021. Another thing that is important ingredient is the layer sum board that sums all the analog readout from the preamp shaper. And for the moment, it's only the schematic that are ongoing, and we will have a test board quite soon. And the radiation needs also to be done on the up amp. So now if I go to the off detector part, This is the last one. We need to apply that digital filtering to digitize waveform, calculate energy and time, and transmit to trigger and DAC. And so for the moment, you see on the right, we have 90% of the routine, which is complete. On this very complex board, you have 2 FPGA that are doing the processing, 1 that is doing the control, and you have 12 Firefly RxTX to do the transmission and reception. For the moment, there are mezzanine that are built to just test the dev kit of the FPGA. And for the moment, there are 6 boards that have been produced for everyone to test that. And the firmware work, which is very crucial in this kind of complex board, is well organized around Git functionalities. There is another component, which is the smart rear transition module. You can see a picture of the dev kit on the bottom, which in fact help the LASP to make data monitoring and etc. So it is going to be tested now.
Narei, can you come to the end? I mean,
yes,
your 12
sure.
minutes are. Yeah.
So just in one word, we have also this timing system that provide the TTC for the boards, and you have a picture of the dev kit for the LPGBT. So on the conclusion, we have seen that most of the ASIC are in the final prototype stage. But also we are starting integrated board design with the front-end board, calibration board, and so on. Just a word that the pandemic situation has caused a few months delay in our project, but still we are on track except for the irradiation testing. And we have developed many ideas to overcome this, for example, with remote access to data acquisition or to moving test bench in people's homes. Thank you for your attention.
Thanks a lot. We have time for a quick question. Is there any?
I have a question, if I may.
Yep, go ahead.
Narei, did you mention where are you going to do the proton irradiation for single event upsets?
So it depends on which ASIC we are talking about. For example, for the low rock, so the front end analog part, and for the calibration ASIC, we are doing this in PSI, in close to zero.
Okay, yeah, thanks a lot.
For the other components, it depends on the country where it is developed. Yeah.
Michal, you also had a question? You had a hand raised?
Yeah, just a question. For your first ASIC, you said it's XFAB HV-MOS. Is it XT018 technology?
Is the XFAB, yes, 109,
yeah,
89.
And is it silicon on-insulator one?
Yes.
Yes, so we have some quite extensive experience with this technology. So you probably use thick oxides, right? Or
yes, we will not use this. You will use this only for half of the, just for the switching part, the transistor part.
Just for the transistor part, yes, okay. So that's the cause of the problem. We have quite extensive experience with this technology, and when you use the thin oxides, the radiation effects are extremely dependent not only on the dose but also on the dose rate. And at 16 grays per minute, we were able to get something like 2 kilorats before the first effects showed.
Ah, okay, so it's interesting.
Remark.
Okay, yeah. Excellent. So we see the same thing then. Okay.
Yeah. Thank you.
Thank you very much, Narei. Then let's continue with Seyedali Moayedi on the upgrade of the ATLAS Hadronic tile calorimeter. Exactly, you stop sharing, and then Seyedali should be able to share. Did we lose him? No. Okay, go ahead, we see your slides. However, we cannot hear yet in case you're speaking. I still see you muted. Can you unmute?
Okay. Hello,
yes.
Sorry. Hello, my name is Seyedali from University of Texas at Arlington. And on behalf of Tile Calorimeter team, I'm presenting my slides on upgrade of ATLAS Hadronic Tile Calorimeter for the high luminosity LHC. So this is the outline of my talk. So I start with an introduction to the tile calorimeter. It's a hadronic sampling calorimeter with steel absorbers and plastic scintillators. Charged particles produce light in plastic scintillators, which is then delivered to PMTs through wavelength shifting fibers. Readout is grouped into pseudo projective geometry cells. Each cell is read out by 2 PMTs. In total, we have around 5,000 cells and 10,000 PMTs in the detector. Calorimeter is composed of 1 long barrel and 2 extended barrels as shown in the pictures. So as an overview of the upgrade project, we will have complete replacement of front-end electronics to provide continuous readout of all channels at 40 megahertz. That's fully digital trigger readout. We will have new back-end electronics compatible with new trigger and DAC system. We will have replacement of around 10% of PMTs, which are associated to the most exposed calorimeter cells. Then we will have our high voltage regulated remotely in the counting rooms and low voltage regulated locally on front-end electronics using point of load regulators. We will also have increased radiation hardness of electronics for high luminosity environment, and we will use mini drawers inside the modules to improve accessibility and robustness of the system. So the expected performance that we have is basically a fully digital trigger system with higher granularity and precision compared to the current system that's going to be used. All data are going to be sent to the trigger system at 40 megahertz. The system requires 2048 optical links at 9.6 gigabit per second from on-detector electronics to the counting rooms. The effective dynamic range of digitization will be increased from 16 bits to 17 bits. For the on-detector electronics, they must be tolerant to radiation effects, especially for on-detector FPGAs, which are sensitive to single band offsets. Triple redundant scheme is going to be considered. Many redundancy levels have been considered so far. Mini drawers are logically split into 2 sides, and each cell is read out by 2 independent PMTs. So in total, in case of failure, the dead region would be 1/8 compared to the current system. Also, aging and significant degradation of some of the PMTs is expected. Therefore, 768 PMTs, which are covering the most exposed cells, will be replaced. So going to the readout electronics, here is just a block diagram. I start with the first component in the chain. PMTs are located inside the PMT blocks, converting the light into electronic signals. Around 10% of the PMTs, as mentioned, will be replaced due to aging. HV dividers are then sitting on the end of PMTs. They divide the input high voltage and provide voltage for the dynos of PMTs. We are going to replace the current passive dividers with active dividers, which provide better linearity for high luminosity environment. Active dividers contain basically transistors and diodes in addition to passive components. The DC current, according to some studies, can go from maximum of around 8 microamps in LHC to 40 microamps in high luminosity LHC. So as you can see here, nonlinearity in passive dividers could go up to 15% in this condition, while it is below 1% for active dividers. So then going to the next component, located on top of active dividers, we have Phoenix board, which shape PMT pulse and prepare them for the ADCs on mainboard by 2 gains, and also provide the slow integrator signal for calibration and luminosity. The gain ratio of the outputs of Phoenix is 40, so we have gains of 0.4 and 16. The selected gains provide the saturation limit of 1050 picocoulomb or 1 TeV for low gain signal. Phoenix boards are replacing the old 3-in-1 cards, which also had analog trigger output signal. You can see here pulse shaping and noise levels for the Phoenix board that are shown. Moving forward, we have the mainboard and daughter board located inside the modules of detector. The mainboard hosts a daughter board which receives data from Phoenix, digitizes it, and passes it to the daughter board. We have 2 12-bit ADCs on mainboard, which provide a dynamic range of 7 bits for the 17 bits for the signals. The mainboard was used in the test beams, and its new version was designed recently, providing voltage and current monitoring for counting rooms. Located on top of the main board, we have daughter board, which formats the data, including detector control system or DCS data, and sends it to the backend electronics through optical links. The optical modules on daughter board provide a data rate of 9.6 gigabit per second for the total 4,096 optical links, from which 2,048 are for backup or redundancy. After using the daughter board in several test beams, the new version is being designed with new FPGAs, Kintex UltraScale, triple mode redundancy, and also improved routing from mainboard ADCs. As you can see here, both mainboard and daughter board are composed of two identical sides to provide redundancy. So then going to the preprocessor located in counting rooms, we have our preprocessor or PPR, which receives data from detector and computes each channel energy and time. Unlike current system with on-detector data pipelines, we are now moving the data pipeline buffers to the PPR, which is closer to trigger system for lower propagation delay. PPR is composed of compact processing modules or CPMs hosting by an ATCA carrier board. After successful tests of PPR prototype in the test beams, which was under development since 2015. First CPMs were made in 2019 and tested successfully using a motherboard. Custom ATCA carrier is also designed to host the CPM and provide connection between the CPMs and trigger and data acquisition interface for TDAC-Chi. So going to TDAC-Chi, it's basically sitting inside the ATCA crate and receives channel energies from the PPR and computes cell energies and quantities to be passed to the level 0 trigger. Digital trigger sums in TDAC-Chi are now replacing analog trigger sums, which was being done previously on detector. First version of TDAC-Chi was made in 2018 and was used to do several tests. Before that, we were using PPR prototype, which was performing the tasks of TDAC-Chi. You can see here that tests were done to verify the performance of board using optical links, specifically Firefly optical modules and SFPs. Then going to the mechanics, all of the front-end electronics are placed on mechanical structures called super drawers, which help us to insert them inside the 3-meter long girders. Mini drawers are designed with half of the length of the current drawers, which provide more accessibility and robustness, and also reduces the scale of a possible single point of failure. You can see here that super drawer design is different for long barrels and extended barrels, as the number of PMTs is basically less inside the extended barrel modules. This tailoring design for extended barrel modules will decrease the number of front-end electronics board as well. Then going to distribution of high voltage. So the regulation of high voltage is basically being done with HV regulation boards in the counting room, which provide regulated high voltage for individual PMTs by considering requirements like noise, ripple, and temperature dependence. Unlike the current system, the regulation is being done remotely, which eliminates the radiation hardness requirements and also provide much better accessibility. Each board provides 48 outputs for individual PMTs in each module. As you can see here, prototypes with 24 output channels were used in the test beams, and recently prototypes with 48 output channels were made. Then going to the LV distribution, located inside the LV box in the finger of the module, we have LVPS bricks, which converted the input 200 volts to provide 10 volt for the front-end electronics, which is then converted to different voltages by a point of load regulator. This is basically a 3-stage system, unlike the current system, which is a 2-stage system. Monitoring of the bricks is being done by ELMB, the embedded local monitoring board, hosted by an ELMB motherboard inside the LV box. Also, the control of the individual bricks is being done via tri-state control signals by the off-detector auxiliary board and through the recently designed robust ELMB motherboard. Then
2 minutes remaining.
Going to the calibration systems. So the two main calibration systems of TALCAL are cesium and laser, which are used to calibrate scintillators and PMTs. Cesium system is composed of the cesium-137 source driven by a liquid through the tiles to deposit known energy on the cells. We'll have new control boards for cesium system, which are designed with a higher radiation tolerance and new type of interface with DCS. For the laser system, which uses 400 clear fibers around 100 meter long routed to the PMTs to feed the laser light to the modules. For them, in addition to new board for control and interface with TDAC and DCS, we are replacing the light mixture with an integrating sphere to add controlled source of DC light to simulate minimum bias events. Here some test beam results are shown with SPS beams and data taken with prototype high luminosity LHC. Distribution of reconstructed energy is obtained for hadrons at different energy. The shower energy show here, E raw, is the sum of energy deposited in the calorimeter cells. We can see lower mean energy due to non-compensating nature of the calorimeter. Energy response ratio and fractional resolution can be found for each particle at a specific energy as defined here. You can see that measured kaon or proton response is around 3% or 8% smaller than pion response. Also measured energy resolution of kaons or protons differ by around 4% or 12% from that of pions. Here we look into the demonstrator insertion. We have a hybrid tile cal module called demonstrator with both analog and digital trigger signals. It was developed and used in several test beams. It was inserted in the detector in July 2019, composed of 4 mini doors in front end with 45 PMTs, legacy 3-in-1 cards instead of Phoenix, and active HV dividers, main board, daughter board, and adder-based boards plus trigger adder cards. These are from the legacy system. We had PPR demonstrator inserted in ATC carrier in the counting rooms, and HV remote system and upgrade LV system. The demonstrator is now integrated in TDAC. You can see performance comparison show lower noise in demonstrator with respect to the legacy modules, thanks to larger dynamic range. In summary, I would say the design of the upgrade is based on the present successful experience. Energy resolution and detector granularity will be preserved. Readout resolution, sensitivity, and dynamic range are slightly improved. A special attention is given to redundancy, reliability, and radiation hardness. Fully digital readout will allow for using greatly enforced trigger capabilities. Improved monitoring and calibration capabilities are also enforced. Extensive tests have been performed of the design with the SPS beam since 2015. The hybrid module demonstrator is backward compatible with the legacy modules and will be included in LHC Run 3. The project has now entered into component production phase. So that's it for my slide. Thank you for your attention.
Thank you. We also have here time for a short question. Anybody has a question? You say you're in the production phase, so was it also hit by COVID? And do you have further tests to do? Is it running fine so far, the production?
Yes, so I think one of the only things that we are still need to do is some just radiation tests that was mainly delayed and affected by the COVID situation. So we are doing the final radiation tests on our LVPS bricks, which are basically located in the most harsh environment in the detector, in the calorimeter, and also some on the front-end electronics with the daughter board FPGAs. Other than that, yeah, maybe there are some minor delays as well, but not that much.
Okay, and you don't expect any surprises from the radiation test since you then want to produce
no,
direct?
So far everything was good, and we had also the backup plans like producing components from single batch or things like this.
Thank you. Then I see Carlos, you also have raised your hand. Go ahead.
So I have a question. You mentioned that the main board will have voltage and current monitoring capabilities sent out. Something like that.
Yes.
Will you be using the GBT DCS bits for this monitoring, or any other?
Yes. This is the plan. The main board is supposed to basically monitor all the local voltages and currents to basically send them through the optical links to the DCS system.
Okay, thanks a lot.
Thank you.
Thanks a lot, Seyedali. then let's continue with Ulrik Egede on the flavor physics for the LHCb upgrade 2.
Okay, I should be almost there.
Yeah.
So yeah.
Perfect. Go ahead.
Yeah. Let's get this one out of the way. Okay, so I'm going to talk more about the physics side of things for the upgrade of LHCb, in particular what we call upgrade 2. So what is the upgrade 2? I think it's the first question.
1 second,
so,
maybe you want to reduce the zoom window, then we can see the full slide.
Yes, if you can see, how do I reduce it?
Sorry.
Yeah. There you go.
Perfect.
Yeah, fine. Good. Yeah. So first of all, what is upgrade 2? So currently upgrade 1 is under installation. There's of course been some minor delays in that due to COVID, but we're well on track. Upgrade 2, however, will first come online in 2032. So this is different to the upgrade schedule of Atlas and CMS. The plan for upgrade 2 is that it will give us 30 times the current integrated luminosity. So you can see here, first of all, you can see how the max luminosity will rise in the red points here. And you can see the curve here that shows us how the integrated luminosity will rise, in total giving us up to 300 inverse femtograms of data at the end of upgrade 2 for LHCb. So I'm not going to talk about the hardware here, but just to tell you what it will involve. So it will involve changes to nearly all parts of the experiments. There will be a new vertex and detector. There will be new hadron particle identification, both through upgrades of the Cherenkov detectors and for the introduction of a time-of-flight detector. There will be upgrades to the tracking to cope with the higher instantaneous luminosity. There will be significant upgrades to the calorimeter, consisting of a new ecal, considering of the removal of the current hadron calorimeter, and there will be upgrades to the calorimeter system. So, in order to look at upgrade 2 for LHCb, I think it's really useful to jump a long time back and actually look at the LHCb letter of intent. This was written back in 1995. And if one goes through it, one sees that observation of CP violation in B mesons and BS oscillations were the main selling points of it. Sine 2 beta and BS oscillations. They were the main selling points. The idea was the CP angle gamma would come from time-dependent analysis of BS to DSK, which would require then that we could see the BS oscillations. The thought was that charm physics could only be done by finding D mesons that were coming from B decays, not by looking at prompt charm at all. BS to mu mu was the only rare decay that was considered, and any kind of physics with baryons was simply not mentioned. That was somehow the starting point of the design of the current LHCb detector. However, the situation that we are in now is a completely and utterly different one. So our first of all, our main point was to some extent taken already by Barber and Bell and D0 and CDF in terms of that CP violation was observed, BS oscillations were determined. But the CP angle gamma is actually a completely different method we're doing now. We're not using a time-dependent method. We're using tree-level decays and penguin decays interference to get this. Charm physics, we get absolutely mainly from prompt production, which has meant that our charm physics program is much, much bigger than was anticipated. And anything related to both rare decays and baryon decays have been vastly expanded. So why did I take this detour here? I think it's important when you go to think about that the main physics that we see right now might not be what we were going to use the upgrade 2 detector for. However, discussing physics is a good method for comparing and contrasting design options. The other thing we should be aware of in comparing to the situation that we were in for designing the original detector to what we're in now for designing the upgrade 2 detector is that the variations in physics we look for are much, much smaller. So back in 1995, we have not discovered CP violation. If you look at the unitarity triangle, we simply had no idea about its shape here. Whereas now we're in a situation where we're looking for slight inconsistencies in where the apex sits within this tiny region here. So it's a very different situation we're in. We're also in a situation where in the coming years, results from BEL2, ATLAS, and CMS might really change our goals dramatically. If BEL2 should discover B to K star and 2 neutrinos, for example, that could really change the way we're looking at rare decays. A discovery of some new heavy particle and ATLAS and CMS might, of course, dramatically also change the way we're looking for indirect results in LHCb. So let me give you one example of this here. So currently, the rare decay anomalies is probably the hottest topic from within LHCb in terms of the B to SLL decays. However, we do have the problem at the moment that it's hard for us to tell if this is new physics or if these are charm loop effects. So if we look at a diagram like the one to the left here, this is a potential new physics contribution to the final state where we have a leptoquark created and we end up with a K star and 2 muons in the final state here. But at the moment, it's really hard to tell us if what we're seeing is in fact not just due to what we call charm loop effects here, where we then have a B to C transition, we radiatively emit a muon pair from that one, and we end up with the same final state. So what we're looking for in upgrade 2 is to go from a situation where we can say it's either one or to the other, to that we can distinguish those two here instead. How are we going to do that? Well, 2 tools that I will mention here that I think are very relevant for this year. One of them is that the same new physics has to fit all measurements. So if we look at the plot here to the right, this is a plot of what we call the Wilson coefficient determined from looking at many different rare decays. Standard model sits down here at the origin at 0.0 here, and we see a whole number of different measurements here. The BS to mu mu measurement is the horizontal band here. We see measurements coming from branching fractions in this one here. We see measurements coming from angular measurements in these here. Different measurements like this here should all lead to a compatible result. There's only one new type of new physics that affects this here because it's affected indirectly. So when the uncertainties of these here are reducing at the upgrade, they should converge to a single point. If they don't, then it's an indication of that it's something we are not understanding in the data. The other one we can look at is shown in the plot down here, which is looking at a single measurement coming from B to K star mu mu, where we measure the Wilson coefficient C9, but we measure it in different kinematic regions of the mass squared of the muon system. So again, these here should give us the same value. At the moment, we can see with the present data that these here are giving compatible results that are different to the standard model that we set up here. But again, is this new physics or not? If it is new physics, we would expect that all these here, with about a factor 5 smaller uncertainty coming at upgrade 2, should still sit and be compatible with a flat line. Whereas if we get something that kind of looks like a tilting line like this here, then we would say, well, it's probably instead some QCD that we're not understanding. Moving on to the unitarity triangle. So the common knowledge that we have used in many assumptions now is that a measurement of the CKM angle gamma is a standard model measurement, even in the presence of new physics. However, it turns out that this is in fact not really true. It's just that, that new physics could just not necessarily affect it in the what we count as electroweak corrections, but this could also be affecting what we count as QCD effect. So the Wilson coefficients that we are associating with QCD. And it turns out that we do not have those under any more control than what we do for the ones that are associated with the B to SLL decays. So the plot down at the bottom here shows how different new physics models can introduce quite large variations to the CKM angle gamma, easily up to plus minus 10 degrees of this one here. We will make measurements of this angle in different ways at the upgrade 2 to better than 1 degree. So it's something that we can really constrain. So what do we need to do? We imagine that we can go from a situation like what we have to the left over here, where we currently see the apex of the CKM triangle here, to a situation upgrade 2 where it's really this tiny point here. That's a different one. How can we make these measurements? How can we look for compatibility here? Well, there's really 2 different measurements that gives us the triangle measurement. One is the measurement of delta MD over delta MS. So we get from oscillations that gives us the orange band here. and combined with sine 2 beta, the angle down here, you get a position of the top point here. The other one is that we measure the CKM element VUB, that measures the length of this side here, and we measure the CKM angle gamma here, which is this angle here. Those two measurements are completely independent of each other. They both require upgrades for statistics. That's how we will improve sine 2 beta angle. That's how we improve the angle gamma. And they also require improvements on the theory side in order to be able to extract what we want from the measurement of the oscillation parts, delta MT over delta S, and in particular for the measurement of VUB, where it is more developments in theory that is required rather than additional amounts of data.
2 minutes left.
Yes. Looking at lepton flavor universality, this is of course one of the other hot points at the moment, for LHCb comparing final states with pairs of muons and electrons. At the moment, we see a measurement here that's different from unitarity, but with quite large uncertainties here. At upgrade 2, we expect to be able to get tiny uncertainties of this here. However, this is something that puts particularly strong constraints on that we need to keep the current performance of our calorimeter with a much higher occupancy. Here, there's no theory uncertainty in this. This is simply a matter of getting more data of high quality. So the final physics point I will make would be on charm CP violation. As I mentioned earlier, charm physics has really grown in importance in LHCb and will do so even more in upgrade 2. So time-dependent CP violation in charm serves as an excellent null test for the standard model. We are very certain that there is no charm-dependent CP violation at a level that's kind of a 10 to the minus 3 level in the standard model. The current uncertainties we have in this are shown by these big bands here. At upgrade 2, we expect to be able to contract that uncertainty by more than an order of magnitude. So this makes it a very promising measurement that comes through changes to the trigger, comes from introducing new tracking stations inside the magnet that allows for lower momentum tracking as well. So that moves me on to the conclusion that the physics case is strong for upgrade 2 of LHCb. There's a note here to where you can find many more details about this. However, in terms of the physics case, I think this should be taken a little bit like a research plan for a PhD. What we present here is a possible direction that the physics will take at upgrade 2, a decade from now, but it's not a rule book for what we can do. Next point is that theoretical uncertainties are significant in many areas, so we need also to work together with the theories on improving that so we can get further understandings of how we can in particular develop clever data-driven cross-checks on theory uncertainties. And finally, maybe that the LHCb upgrade is ambitious, but that we should not compromise too early on it, because then we might simply not know what gains we can make. So just to finish, I also have a performance table here. You can look at this one for specific numbers of estimated resolutions and so on, but I will not go through the numbers. So thank you very much.
Thank you for your presentation. Are there questions? I don't see any hand raised. Then I'm curious, you just mentioned that there will be also, of course, new detector parts. Can you say a little bit more on this? So that your new tracking station, I guess you can imagine show us in this session.
So so in terms of the tracker, we're currently installing a scintillating fiber tracker that's replacing our current one that's based on straw tubes. That will serve us even in upgrade 2 for the outer parts of the detector, so the ones at low pseudo-rapidity, whereas very close to the beam pipe, we will have to replace those by a silicon detector. So that's in the region after the magnet. I'll just get back to the plot here. So in the region we have here, these here, we will introduce that. We will introduce tracking stations that will sit on the inside of the magnet here. That's a way that we can improve our efficiency by having also ability to do tracking, where we get measurements going through the magnetic field for lower momentum particles. So this is more an upgrading capability than an upgrade that's enforced by higher luminosity. The rich detectors, so the Cherenkov detectors we use for particle identification, there we will need to have new photon detectors that can cope with a higher occupancy in them. And then we will also hope to be able to introduce what we call the torch here, which is a detector. It again works through Cherenkov light, but it has a very precise timing in it. So the idea is that we simply can do time of flight measurements from down here up to here that will be able to give us hadron identification at very low momentum, something that we've not had in LHCb so far.
Thanks. Then I would like to thank you for the presentation, and we go on with Zach Schillaci on the tracking performance for the Halumi ATLAS detector.
Yes, hello everyone. Let me share.
Very good.
Everyone see my slides?
Very good.
Great.
Yeah, we can see and hear.
Thank you. So my name is Zach Schillaci, and today I'm happy to share some tracking performance studies of the high luminosity LHC ATLAS detector. So I don't think I need to spend much time explaining the ATLAS detector, or really the high luminosity program, thanks to the previous talks this session, but I'll just give a quick overview for purposes of motivation of high luminosity. So the high luminosity program is really the ultimate run of the LHC. It's beginning sometime in the late 2020s. The center of mass energy will be increased to 14 TeV and will be running at unprecedented instantaneous luminosity, which will yield us an enormous amount of data. So we plan to run this program over a decade, I think we're thereabouts. And this will yield something like 4,000 inverse femtobarns of data, which, to give you some scale, in run 2, the previously finished run, we collected up to about 140. So this is a huge increase. Of course, with these conditions, we're going to be dealing with a difficult environment. So we expect on average 200 proton-proton collisions per bunch crossing. This is what we call pileup. And this is what I show in the plots below. So on the left is what we've had so far across run 2, where our average pileup has been sitting around 30 or 40. And at high luminosity, we expect something like 200. And this is a sample simulated event display at U of 200. So of course, to cope with this challenging environment, the ATLAS detector must be upgraded, as you've already heard, to maintain the high performance requirements. And on slide 2, one such upgrade is the new inner tracker, or ITK for short. This is a complete replacement of the current ATLAS inner detector, which is our current tracking detector, as you could guess. I linked to more in-depth talks on the actual design and sort of the layout of the detector for both the pixel and the strip system, which are also iChep talks. So as I've said, it's also, well, it's a pixel and strip tracking detector, so it's all silicon. I highlight in red the pixel inner tracker and the outer strip detector here. You can see the coverage extends to a pseudo rapidity of 4, which is an increase from 2.5 for our current tracking detector. It has a finer granularity and improved radiation hardness, which is important for the high fluence expected in the high luminosity program. Going on to slide 3, so the layout of the ITK is such to guarantee a hermetic coverage within the full tracking acceptance. What this means is we expect at least 9 hits on track for all particles above 1 GeV within this a reasonable vertex window. This is shown here for single muons with 1 GeV. So with this pretty tight coverage, we were able to tighten our track selections without compromising much on the reconstruction efficiency, which is very important if we want to maintain high efficiencies with low corresponding fake rates in these track dense environments of high luminosity. I also outlined some quick facts of the current tracking detector. So one thing I alluded to before is that the coverage only extended to 2.5. So we're really gaining a lot in forward coverage with ITK. On slide 4, this is just the last slide on the design of the ITK. So of course, for tracking detectors in experiments like ATLAS, it's very important to have a minimal material budget. This minimizes effects of multiple scattering and energy losses before the outer detectors. And thanks in large part to the all silicon design of ITK, we've really been able to reduce the material budget, especially in the forward region. This is shown, so a comparison ITK versus run 2 here. What we're seeing here is the essentially the nuclear interaction likes traverse before we satisfy the minimum hit requirements. And actually these hit requirements are tighter for ITK. They're outlined in this table here. And compared to run 2, where we just had a flat requirement of 7, we're able to actually tighten these selections. And as you'll see coming up, this doesn't really hurt us in efficiency of the fakes. On slide 5, this is just intended to give a brief overview of the reconstruction challenges. So the typical tracking chain for Atlas follows essentially a 3-step process in which in the first step, seeding, what we call seeding, is where we search for hit triplets of 3 space points. From these, this collection of seeds, we run the track finding with a combinatorial Kalman filter, which gives us our track candidates. And finally, in the last step of ambiguity resolution, we do a global chi-squared fit, and the track cluster assignment is run once again to based on a scoring algorithm to finish this. Now, as you could imagine, in a track dense environment with expected 200 pileup vertices, this is challenging because of the combinatorics involved. So the design and the reconstruction of the ITK have been really optimized with this track dense environment in mind. And what we see here on this plot is if we focus on the black solid line, this is the total ITK reconstruction time plotted versus the pileup. And the black dotted line is the same for run 2. And given the improvements made so far, we actually see that the reconstruction for ITK at a pileup of 200 is already faster than run 2 at 60. And of course, since this is far out, there are still many improvements ongoing, which will further speed up the algorithms, but already we're in a very good position. On slide 6, we start to look at the performance results, starting with the usual efficiency in the top right and fake rate in the bottom right here. In blue is the ITK. I should say this is for TT bar samples. So in blue is ITK at the expected pileup of 200. And in black is the run 2 detector at a pileup of 20. So that's important to keep in mind, this large difference in pileup between the two plots. And what we see for the efficiency is, given this difference in pileup, we still have a comparable efficiency, and we maintain over 85% throughout the full tracking coverage. For the fakes, we see quite a remarkable improvement where there's about a factor 10 reduction, even given this factor 10 increase in pileup. Now, this is thanks to several things, probably most notably the increase in overall hit counts, which I said before allows us to tighten our track selections and really reduce on fakes. And of course, you see that the forward coverage extends for ITK beyond 2.5 all the way to 4. Going to slide 7, we look at the transverse impact parameter resolution. So this is the distance of a track's closest approach to the beam spot along the transverse, which is the XY plane. We call this D0. If we focus on the right plots, this is showing a comparison of the ITK with the run 2 detector. There are actually 2 instances of the ITK in green and blue, given different pixel pitches. But if we focus on sort of the 50 by 50, which was the previous nominal layout of ITK, and if we look at high PT here, where we're actually driven by the intrinsic detector resolution, we see that the resolution is roughly comparable, but there is a bit to be gained if you go to the 25 by 100 pixel pitch. And actually, since these plots were made, a change was made in the layout of ITK, in which the innermost barrel layer of the pixel will be switched to this 25 by 100 pitch, which lets us gain a bit compared to the green resolution here. There are also changes in the inner pixel layer radius, which would also help this. On slide 8, we look at the orthogonal transverse impact parameter. So orthogonal to the previous one. This is I shouldn't have said it that way. This is the longitudinal one. It's along the z-axis, but it's orthogonal to D0. Here again, the plots are laid out in the same way. And if we look at high PT again, we see significant improvements with respect to run 2, actually regardless of the pixel pitch chosen. Now, this is good to see because getting Z0 accurate is really important for both pileup mitigation, which is a big challenge of high luminosity, as well as vertexing in these high density environments. And speaking of vertexing on slide 9, so what I mean by vertexing is the process of both reconstructing and identifying the primary hard scatter, as well as the pileup vertices. Now, as you could imagine, this is difficult given a high pileup environment. You have many meter by vertices, vertex dense environment, which must be individually resolved. So some improvements had to be made actually to the vertex fitting algorithm. So we're using a modified version of the Run2 iterative vertex finder. This is called the adaptive multi-vertex finder, which allows for some simultaneous fitting of vertices if tracks are assigned to more than one vertex. And now if we look at the reconstruction efficiency of vertices on the left plot, again, we have these two instances of ITK based on the pixel pitch, but they're nearly identical in this case. And what we see is that not only is the baseline efficiency improved over Run2, but the stability with pileup is much improved, such that there's almost no degradation with pileup. But this is similarly true for the vertex resolution on the right, where again, the baseline resolution is improved and there's practically a flat dependence with the pileup density.
2 minutes left.
Thank you. On slide 10, this is just a brief overview of the physics objects. I'm not showing everything, of course, but just to summarize both these plots and ones that I'm not showing, I could say that there are excellent prospects for future developments in the realm of both object reconstruction as well as combined performance for the high luminosity LHC. In the bottom left, I start with the pileup jet rejection, where there's particular improvements in the forward region. This is comparing the green dotted, which is Run2, with the green solid. Of course, this is in part due to the Run2 limited coverage. The muon track isolation efficiency shown in the middle is shown to be both stable against the local pileup density. So this is essentially just the vertices per unit length, as well as the global pileup, which is just the number of pileup vertices. And lastly here for B tagging, which is, if we look here, it's essentially comparable. So Run2 is shown in pink and the comparison is shown at the bottom. It's essentially comparable performance at this stage, but again, this is a large difference in pileup, and there's large room for improvements here from ITK specific optimizations. So to conclude, the ATLAS in our tracker, the ITK, is well designed to cope with the track dense high luminosity environment, has an all silicon design, has finer granularity and the extended forward coverage. And it will really be key to the continued success of ATLAS during the high luminosity program. The reconstruction has been optimized and is continually being optimized for this difficult environment. And we're already seeing improved performance in many ways and comparable performance otherwise, keeping in mind that we're now working at a much higher pileup. And one thing I've yet to mention here is that we'll also have track time assignment possible with this new forward timing detector. This is called the HGTD, high granularity timing detector, which will allow us to further improve the pileup rejection. So thank you. That's all I have.
Thank you very much, Zach. Are there questions? Can you comment on impact of varying material? So I guess here for the simulation, a certain amount of material is assumed, but now when the detectors are built, maybe there's more material. Where is the biggest impact?
Yeah, of course. So this is something that's always in flux given collaboration with the engineers. And so we've done many studies of material variations in the PP1 region, which is actually coincidentally around this region where we varied it by 10 to 20%. And actually the performance studies you saw for many of the plots here is with, as of the spring, the most up-to-date layout of the ITK, which had more material than previously estimated in the beginning, but we still have very good performance and we haven't really lost too much on the resolution or the efficiencies there. But this is something we'll keep studying because it's likely to change again.
Thanks. Anything else? Then Zach, thanks a lot for your presentation.
Thank you.
And we continue with Benedikt Bergmann on the development of a penetrating particle analyzer for high energy radiation measurements in space. Hello, we can already see you.
Okay, hello everybody.
Okay, perfect. Go ahead.
Okay, okay, so thank you. So I'm going to discuss the development of a penetrating particle analyzer, especially for high energy radiation measurements in space. So we are leaving the Earth now and look into instruments for space research. Penetrating particle analyzer is long for PAN. And the PAN consortium consists of researchers of University of Geneva, the INFN in Perugia, and the Czech Technical University. Yeah, what is PAN? So PAN is a future scientific instrument which is dedicated for deep space and interplanetary missions. And its goal is to precisely measure the flux composition and direction of penetrating particles, which are actually defined as particles which have more than 100 MeV per nucleon. Such particles can be found, for example, in solar particle events. However, these TeV solar particle events are rather rare. But of course, these are the ones which are potentially harmful. Moreover, there is a steady flux of galactic cosmic rays, and this is actually dominant at high energies, so it has a peak at roughly 1 TeV per nucleon. So to summarize, we want to measure the TeV particle flux because it has not been measured precisely in situ in deep space. So the science goals of these instruments are to contribute to cosmic physics. So as I said, there is this observation gap for galactic cosmic rays, but this can help to understand the origin of galactic cosmic rays and how they interplay with solar activities. Moreover, we will be able to contribute to antimatter searches, so to measure the content of antimatter in these galactic cosmic rays. Then we would like to contribute to solar and space weather modeling. So measuring these particles can be a good input for improving the models which are currently used. On a more life science approach, we could also contribute to planetary science. So if you use this device on a planet, you can measure the radiation environment and evaluate if it's good for being a future habitat, or as kind of dosimeter on deep space travel missions. So if you want to save the astronauts, it would be good to have estimations of the doses. Of course, measuring TeV particles is not so easy. So typically people in space use the delta EE method. So which means basically you have a calorimeter and stop the protons. But in order to stop a 1 TeV proton, you would need something like 170 centimeters of silicon. Moreover, the nuclear interaction length of silicon is 50 centimeters. So which means that in this 170 centimeters, it's more probable to create kind of hadronic showers and don't stop the particles just by better Bloch losses. So this means you would get a bad energy resolution. So the calorimetric approach would mean you have a very thick device and you would have an energy resolution which is around 30 to 40%. So our idea is to do it with a magnetic spectrometer to measure the bending radius and the bending angle. And this is illustrated here. So we think we would use 4 sectors. Each has homogenic magnetic field in this direction here from up to down on this plot, so that the particles are bent perpendicular to the plane of the presentation. And in each of these planes in between, we would measure the positions and also the energy lost in strip detectors. So from a technical viewpoint, so this is a cut drawing of the device. At both ends of the device, we have a baffle, which is followed by a time of flight module, then the pixel detector and the tracker module, and then we start these magnetic sectors. The pixel module, we will use either Timepix 3 quad or a Timepix 4 detector. So we will have a silicon sensor with 55 micrometer pixel pitch. For the tracker module, we want to use 2 strip X detectors, which have a pitch of 25 micrometers in order to get the resolution around 2 micrometers. And this tracker module also contains a strip Y plane, which is used then for measurement of the charge. and this has a pitch of 500 micrometers. The central planes, they're a bit reduced, so they only consist of the tracker module, which means the 2 strip planes and the strip Y plane. The design goal of this device are to have something which is light, which can operate at low power, and also the design is symmetric, so we can measure particles coming from either side. With this time of flight module, which is basically a scintillator, which should have a resolution around 100 picoseconds, we also want to estimate if the particle comes from the left or if it comes from the right. The magnetic field is created by permanent magnets in the so-called Halbach geometry. So the diameter of these devices is 10 centimeters, and the length of these sectors is also 10 centimeters. So we would create a dipole magnetic field of around 0.2 Tesla. So this is shown here across the instrument. Yeah, so now the expected performance, mainly in terms of energy resolution. So what you see here is the relative energy resolution as a function of the kinetic energy per nucleon for particles crossing different number of sectors. So of course, the best energy resolution we get if the particle goes through all 4 magnetic sectors. And in this case, we can get an energy resolution which is better than 10% for particles from, let's say, 0.4 to 20 GeV. Of course, if you have particles crossing less sectors, the energy resolution gets worse. So the worst case is shown here on the right if the particle crosses only 1 sector. And in this case, we have something like 20% for protons if they are below 2 GeV, or in the range from 0.2 to 2 GeV. Okay, now we have applied for funding to create such a device and send it to space. And with PAN, we were not successful, but we got funding for a so-called mini PAN, which is a reduced version. And we received funding from the Horizon 2020 call. So we started this year in January with preparation of mini PAN. And this is a device, as I said, with smaller dimensions. So it consists only of 2 magnetic sectors, which are also reduced in size. But this device should be suitable for space weather analysis because it's small enough to put it even on CubeSats. And of course, also you can think about using it for this planetary exploration. Even though it's smaller, it still has the same instrumentation as the full PAN. So this should be a demonstrator that the technology could work. And if it's successful, we would like to continue with preparation of the full PAN system. Of course, the less sectors means worse energy resolution. So here we show the energy resolution for 2-sector acceptance. So what you see here is that the energy resolution, or relative energy resolution, is better than 20% for protons of 0.2 to 10 GeV, which is roughly here. In order to get these values, we increased the magnetic field strength to 0.4 Tesla. Moreover, since we are considering to use this in kind of low Earth orbits on CubeSats, we are thinking to add some delta EE detectors in order to have a particle monitor, which is actually sensitive to a bigger, broader particle energy range. Okay, so I can show already some results from this project. As I said, we started in January. So we started with purchasing and developing some magnet prototypes. This was done together with CERN. We have now 3 of these prototypes, and the testing started in January. It was then interrupted, unfortunately, by the Corona crisis, but we can show some first results. So a picture of these magnets is shown here. So we have 5 centimeters of diameter. Magnets are surrounded by this aluminum ring. So this keeps them basically in place. And the first test show that the central field is 0.4 Tesla and that we have a field homogeneity of around 10%. Moreover, we were working on the pixel module. As I said, the pixel module is either Timepix3 quad or Timepix4 detector. So we will have around 260,000 pixels with a pixel pitch of 55 microns. These detectors allow to measure simultaneously the TOA and the TOT in each pixel. And for the moment, we have a sensor thickness of 300 micrometer. But we will probably use in the final device a sensor thickness of less, so around 150 or 100 micrometers. The main challenges for the pixel module are that the power consumption is rather high. So currently we are working this quad at 6 watts, but the goal of this space is always to have low power consumption. So we have to try to reduce it to something below 3 watt. Moreover, the temperature management is a bit tricky. So if you use this device without cooling in air, you will get around 80 degrees at the sensor or at the pixel electronics. If you would put it to vacuum, it even increases to around 120 degrees. So also we have to find a solution how to easily remove or quickly remove the temperature from the ASIC.
2 minutes are remaining.
Okay, thank you. On the other hand, we could already do some first test measurements also here in the Czech Republic at Rzesz, where we had helium-3 particles of 36 MeV. And you can see just some example response when we have the helium impacting at an angle of 75 degrees to the Timepics3 quad. Okay, so then short summary and outlook. So PAN is a future instrument for precise measurement of the particle fluxes of these highly penetrating particles for deep space and interplanetary missions. For the moment, we received funding from EC for the mini-PAN, which would be used as technology demonstrator. And we are currently in the year 1, which means we are working on the design of the mechanical and electrical structures and also to improve the CAD models. In the next year, we will be working on finalizing the development. And in year 3, we should assemble all modules and do some verification tests and space qualifications. So far, we have already started to look for flight opportunities, which is then a kind of valuable or valid from 2023. And we are considering the use on the Lunar Gateway, some CubeSat missions, or the use in Jupiter radiation belt exploration, or on the European Large Logistics Lander. And yeah, with that, I thank you very much for your attention. So we hope that 2023, we will see this device flying in space here and measuring particles from coronal mass ejection.
Thanks a lot.
Very much.
Thank you. I see Michelle, you raised your hand. Go ahead with the question.
Yes, I have a question. With such a magnetic field configuration, do you plan, or how do you plan to keep orientation of the spacecraft in low Earth orbit? Because then it would clamp to geomagnetic field and you won't keep your orientation easily.
You mean that that we would kind of disturb the magnetometers on the CubeSat?
No, that you have a strong magnet which will orient the instrument according to the geomagnetic field in low Earth orbit. So it will keep, attached to the magnetic field lines and rotate.
Okay. Okay. Actually, I haven't thought about this, but that's a good remark. So you should look into that. Yeah.
Yeah, because it would keep rotating, I would think.
Yeah.
Then Seyedali, I see also you have raised your hand. Go ahead with your question.
Hello, yes. So please, on slide 12, I have just a question about this picture with the temperature map. So do you know which component is it here that you show that has the highest temperature?
This one which has the highest, I guess it's some power supplies. Because
on the back side of the board.
Yeah.
Okay.
Actually, these temperatures are not real. It was not calibrated, so it was just a relative measurement, just to see where we have the highest contribution from.
Okay, thank you.
Yeah. Since we're on this page, you mentioned here the challenges of the power consumption. Can you give details what you try to reduce it? Yeah.
So what you can do with Timepics3 is to play a bit with the configuration of the Timepics3 ASIC. So you can change some DUC values, and also what you can change is the readout frequency or the clock frequency. So if you now I say we have a TOA binning down to 1.56 nanoseconds, but if you want to reduce the power consumption, for example, you use not 640 megahertz clock, but you can use 5 megahertz clock, which is still reasonable for space because the hit rates are quite low there. And then you can already reduce the power consumption significantly.
Okay, thanks. Then I would like to thank you, Benedikt, for the quite clear presentation. And we go on with Qun Ouyang on the development of high resolution, low power silicon pixel sensors for the CPEC vertex detector. We couldn't try before. I hope technology works fine for you. We can start sharing.
Hello, can you see my slides?
No, we can only hear you. Now we can see the slides. And maybe you go to full screen.
Okay.
And probably speak a little bit up. Your very low voice at the moment. At least for me.
Is that okay?
Okay, then go ahead. And yeah.
Okay, sorry. And thank you. And I'm happy to be here to speak about something about the development of high resolution and low power consumption silicon pixel sensors for the CEPC vertex detector. And I will see a little bit about the requirement for the CEPC vertex detector, and then followed by some recently developed pixel sensor prototypes, and say something about the planning of our consideration for the next step. And for the CEPC vertex detector, the efficient tagging of heavy quarks and have very stringent requirements on the pixel sensors, especially for the innermost layer, should be very small pixel pitch, and like the ILD design in the CEPC in C conceptual design report, the CEPC vertex detector has the so-called double-sided concept, but without the power parsing mode, and especially for the innermost layer, and the point resolution should be better than 3 micron, and so the pixel pitch it's about 16 micrometers, and also with very small material budget and low power consumption, and almost faster readout, especially for the the CEPC will operate and in Z0 mode. And there is already some R&D activities for the CEPC vertex silicon pixel R&D activities, and the one is based on the TowerJazz 180 nanometer process, the CMOS process. Another is the SOI pixel based on the Lattice 200 nanometer process. Both CMOS and SOI R&D, firstly, we will focus on the fine pitch and the low power front end pixel design, and that's why we have some CPV series sensor prototypes based on SOI process, and the JPX prototypes on CMOS process. Besides, we have to consider some faster readout architecture to meet the occupancy on the experiment, and we already have a MIC4 prototype on that. But some of the prototype developed already reported in the HL conference 2 years ago. So right now I will see something about the SOI 3 and the CPV 3 on SOI and the JPX 3 on CMOS. This slide shows some the prototype developed for by different years, and starting from 2015, and I have to explain here. And we have for CEPC vertex detector, we have another team. These started the pixel sensors with faster readout and 25 nanosecond timestamp, especially for the Z0 operation mode. And also they will develop double-sided prototype. But those will not reported here, and I will see something about the CPV3 and the JetPix3. CPV3 is designed with the so-called SOI pinned depleted diode process. That process, PDD process, was proposed by our Japanese colleagues with many good features and to reduce the surface current leakage and also some good features for the reduction of diode capacitance and the improve the charge collection efficiency. And CPV3 is our first try to use the SOI PDD process. And for the PDD process, one issue is the relatively large diode capacitance dominated by the gap between BNW1 and the BPW1. So at least 4 positive 4 volts, the biased voltage could gain a gap to reduce the capacitance less than 4 ferrofarad, and that's our solution is we will use a positive biased voltage to the BNW1 and the diode is AC coupled, not DC coupled, AC coupled to the in-pixel circuit. So we want to have a larger biased voltage to give a smaller capacitance of the diode. And the sensor has a common source amplifier and cascade as the second stage, and also as the discriminator. By the simulation result, the fixed pattern noise is about 12 electron charge. And I have to say, and for the previous CPV2, we measured the fixed pattern noise is about 115 electron charge. We do have some sensor test. First, we will try to verify the leakage from for example, for Flavour and the BPW, and also we can from this plot you can see when the diode voltage applied to 4 volts and the leakage current on BPW and the peripheral and significantly decreased, and so that we can choose that the working parameters and the test with the ion source, and we can calculate the equivalent for the diode voltage at 4 volts. We can have the capacitance of the diode is about 12 femtofarad. This is the verification of the diode capacitance reduction with the increase of the biased voltage, and you can see from the about 3 volts and to 8 volts, the capacitance CD decreased. However, comparing with the simulation study, and we had an expectation to be about 4 femtofarad at 4.4 volts, but the measurement gave the results about 12. That's means we have should have some parametric capacitance from the routing in AC capacitor and the input transistor, and this is partially confirmed by our simulation results. So since we have lots of metrics on that CPV3 sensor, and next we have to do some more tests for the different structure, and especially the noise and threshold measurement for the whole matrix, and then the beam test sometimes in the future to verify the spatial resolution. And speaking of the JetPix3, that's the first fully functional prototype with small pixel sensor and with the TowerJazz 180 nanometer process. The specification is we want to reach around 3 micrometer spatial resolution, and the fixed pattern noise for the whole matrix could be below than 20 electron charge, and also the power consumption restraints. And the chip readout is the rolling shutter mode, and so about 100 microseconds to finish whole matrix read.
So 2 minutes remaining.
Okay, thank you. And the diode and the front-end design is we have lots of optimization for the string the area design, and so the chip already here in May of this year, and we need to do lots of tests. The estimated of the power consumption is about 55 milliwatts per centimeter square, and the smallest pixel layout is 16 by 23 micrometer square. And for the next step, we have to do some more optimization for the CEPC vertex system, especially for the increasing luminosity in the Z, especially in the Z-pole mode, and the development of the CMOS sensor with faster readout and timestamp. And at the same time, we have to explore some new process. I will see something about SOI 3D process, and also stitching CMOS process. SOI 3D is processed by T-Macro foundry T-Macro in Japan, and we had a lot of experiment from our Japanese colleagues, and especially the Sophist 3 chip for the IRC experiment, and they have measurement of the good connection yield. For the CEPC, we have want to have some faster and low power consumption design, and the timing is about 1 microsecond, and the power consumption and also the pixel area. The first prototype CPV4 3D will be submitted around November of this year. And another interesting is the stitching CMOS technology, which was for the ATLAS ITS3 upgrade with very good features. And we had some fast simulation result for if we use some a much smaller material budget for the CEPC vertex detector, and we can also reach the impact parameter for the physics. And also in CCNU, Central China Normal University, and IHAP, there is a joint effort to explore such kind of process in China. Okay, to summarize, I will not say lots about that. And the only one issue is I have to mention a pixel vertex detector prototype will be built within several years, but as it was not covered in this talk. Okay, thank you.
Thank you. There's time for one short question. Anybody want to raise anything? Can you comment where you do your beam tests?
Yeah, we did have some plan to do the beam test in the end of this year or early of next year, but so the COVID-19 pandemic, and we got some influence for that, and probably could be delayed, I don't know, in half year or 1 year. This is a problem.
Thank you. Then I propose we go on with the next presentation by Piero Giubilato on ARCADIA, an innovative low-power large area maps for HEP and applied science.
Okay, hello everyone. I'm waiting
Ouyang, if you please stop sharing.
Okay.
to share my screen. Okay, thanks.
Yes, we can see and hear you. And the slides are coming, yes, and go to full size.
Here we are.
Yeah, go ahead.
Okay, thanks. So first of all, thanks for the organizer for the invitation. And I'll try you to briefly show what we are doing within the ARCADIA project. So ARCADIA, as you can read, stands for, is an acronym standing for Advanced Readout CMOS Architecture, which is one part of the project over a depleted integrated array that is the second highlight of this R&D. This entire R&D is supported by INFN Italy, and as you can see, there are many people contributing to it. So what we are speaking of? We are speaking of monolithic active pixel sensor. And in particular, we did start this R&D with the aim of developing design and fabrication platform. So we are not targeting a very specific experiment, but more in general, we gathered the necessity from various fields, and we tried to find a common, sets better of common requirement to justify an R&D development to address this common requirement. So if we look, we did start from medical application, so medical imaging, specifically medical imaging with ions, so proton or ions. And in such case, we can see that the most stringent requirement as we deal with really highly ionizing particles, so highly scattering particles, is to have very large area detector because we cannot afford the support structure. So we need a pixel detector with very large area, so many square centimeter, and very thin. Then if we look at future lepton collider, either E+, E-, or even muon factory collider, we see that in such case, we have, again, thin detector, so low material budget, but higher flux, particle flux, so in the order of 100 megahertz, and a medium to low radiation tolerance of some about, let's say, 10 kilogray. Furthermore, not to be forgotten, quite the contrary, in space application, we can definitely relax our constraints about the rate, which is usually very low, and even about the radiation tolerance that is very modest. But definitely here the highlight is the power budget, that here I place that better than 10 milliwatt per square centimeter to be compared with the hundreds we have in the present generation of LHC pixel detector, or even with the around 40 that we managed to have in the ALICE experiment, or as we saw from previous presentation is foreseen for lepton collider. Here I put 10 milliwatt, but we could even say that 5 milliwatt would be much preferred by the space community because this is the constraint of the spaceship. So the tables here summarizes these requirements. So in our R&D, we did set this specification for our sensor. As you can see, maximum power consumption is of the order of 20 milliwatt. The matrix area, we are aiming high, so that would be almost full wafer sensor, but to be realistic, we will start with a much smaller demonstrator of 1 square centimeter, and we are aiming at full reticle size by next year. And the heat rate is on the order of 100 megahertz square centimeter, assuming that for each heat we'll have on average 4 pixels per cluster highlighted. Of course, it's a binary readout. Pixel pitch is as a maximum, so we settle for the moment on 25 micron, mostly because from tests this result in having a full charge collection efficiency, even with the small electrode, the collection electrode we want for keeping the capacitance of the detector low. Last word about radiation hardness. At the beginning, we will aim for something like 5 kg because this is the exportation limit for military rules. So if we want a detector that we can use in other applications that is not just collider, it's better to stay clear from limitation on exportation. In case we can clearly look for a special version for colliders. So first about the sensor. The sensor, actually, we did start from our previous result that we managed to obtain during the SIT project that was another INF project, a precursor of ARCADIA, where in collaboration with LFoundry and using 110 nanometer CMOS technology, we develop and patent a special double phase process where we have implantation with 4 masks in the back side of the wafer. So you can see on the right, we have a wafer where we have a high resistivity substrate, and then we have some implantation on the back. The process has been developed by LFoundry and patent, so they are able to implant the top, then reverse, and then perform a realign and do implantation on the back. That patterning on the back, and basically interesting is to say that with this we can assess to thicknesses of the substrate from 50 to 500 micron. Actually, we did run with 100 and 300 micron thicknesses that we tested, but in principle we can assess this different range of thickness. So thanks to that, here I reported we can see that this is for the 300 micron thick detector that is more interest for high energy physics. For example, you can see a slice of the depletion growing within the sensor, and on the right there is of a small test matrix the voltage of the collection node after reset. As you can see, until we get full depletion to the corner of the matrix, we have a connection with the ground ring you can see on the border of the matrix. So the reset is not properly working, so we cannot reach full depletion. But when we increase for 300 micron, for example, to 140 volt, then we have complete depletion across the entire matrix. Of course, if we look at the 100 micron thick detector, that we achieve with 60 volt, that is much less. Furthermore, we did perform some testing with total ionizing radiation. And here you can see the gain of the front-end stage respect to the total dose, as well the noise measured in electrons. The different color represent different flavor actual layout of the collecting node of the sensor test. Anyway, the variation is small between the different design, and as you can see, the trend show that the gain of the front end stays almost uniform, well up to 1 megarad, so 10 kilogray, and the noise increases by 50% up to the 10 kilogray or 1 megarad level. That is a nice result for such kind of detector. Actually, we perform neutron irradiation with slow neutron from reactor And we are completing the data analysis. The COVID-19 crisis did slow down a bit the things, but nevertheless, that is well in progress. Now, this was for the sensor that, so to speak, is proven now and established. And we had to come up with a readout architecture that is the main purpose of this project, that is flexible and scalable because we want to read large areas. So the first demonstrator that is going into the foundry for production contains two 512 by 512 pixel matrices. So the matrix is 500 by 500 pixel, but the architecture has been designed to actually being able to read columns up to 2048 at least pixel, because that's what will be necessary to read these 4 centimeter tall columns. As you can see, the two matrices are identical except for the front end. So on one we have an Alpide-like front end, while on the second one we have a different front end that tries to improve on power consumption with respect to that. So here it's a layout thanks. Of the matrices, the main matrix, and then at the periphery we have the usual bias block readout register section. Pixel is 25 by 25 micron, and the matrix is divided into, as you can see, 16 blocks, identical blocks of 32 by 1512 pixels. As I told you, we have these two matrices. One has an Alpide-like front end, you can see on the left. The other one, sorry for this 300 micron, the pixel is 25 micron, of course, not 300 micron. That is wrong arrow. And on the right, instead, we have this so-called bulk-driven front end that has a different layout respect to the left one. The diode area is 9 by 9 square micrometer, and the available area for the analog electronic is around 220 square microns. How is organized this matrix? Is organized, as I told you, in 16 sections of 32 pixels, and the 32 pixels are organized in double column, and on the right, the double column are organized in pixel region of 16 times 2 pixels that are called cores to optimize the communication across the column, so the repeater for the long column signal. Each group of 32 pixel column has its own output that runs at 320 megabit per second. So if we look now more in detail at the column, we see that we have a completely asynchronous readout, and the pixel, the cores, are organized in a master and slave unity that talk asynchronously one to each other. To make it short, which is the concept that only the master are actually connected to the periphery of the column and can move data from the pixel to the periphery in case they have a need. The slave can just contact either the master they have on top or bottom and ask for their data to be sent. Which is the purpose of this arrangement? It is that within the double column that you can see sketched here in the middle of the slide, for all these cluster configuration, the green, the red, the blue, the yellow that represent few of the possible cluster we may encounter, actually only one of the master transmits the data, so highly optimizing the data packet that is sent. That allows us to save many 10% on the bandwidth to the periphery of the column.
May I ask you to come to the end of your talk?
Actually, this is in fact my last slide. So this is the output, and the only note that I have is that among the 16 section, in case we want to operate it in even lower power, we can skip the output and collect all the output to a single transceiver, and this is so-called the space mode, where we save clearly all the transceiver power except for one. And that, going to the conclusion, apart the verification, that we have a complete set that allow us to inject realistic cluster and check the performance. So the next, this is a summary of what we saw. So for the next prototype, this one is going into production. We will try an even more efficient architecture, quite innovative to be tested. And we will add the protection against a single event upset that at the moment is missing. And then by the end of next year, we will go for switching to really test the large area detector, and that was my conclusion.
Thanks. Is there any urgent question? Then Piero, thanks a lot for your presentation. And I would like to propose to go on with Carlos Solans Sanchez on the radiation-hard monolithic CMOS sensors with small electrodes for the high luminosity LHC and beyond.
Can you hear me?
Yes, very well.
Can
and
you see me?
Perfect. Yes, and go
Very
ahead.
Good. And now there was this trick to make this thing full screen. Okay.
Yeah, perfect.
That should be working. Okay. How can I make this thing go away like that? Okay. Okay, so I'm going to talk to you a bit about, by now you know already what is going to happen by the high luminosity LHC, which comprises a series of upgrades called phase 1 and phase 2 to exhaust the physics potential of the LHC. Okay, but we also want to focus on what's going to happen beyond that, right? And for this, we know that the FCC was recommended by the 2020 upgrade of the European strategy for particle physics. Okay, and what we want to propose is we want to propose the usage of monolithic pixel detectors that would cope with radiation exposure and high pileup. Okay, so before we get started, let me show you nice pictures of the hybrid pixel detectors that we find today at the LHC that will suffer major radiation damage before even we start the high luminosity LHC. But what are monolithic CMOS sensors? Well, these are industrially produced pixel detectors. And we are interested in focusing on those that have small collection electrodes, which are the ones on the top. The electronics are outside of the collection well. They have small capacitance, they have high signal to noise ratio, and a large drift path. This has to be compared with hybrid detectors that we find in the center of LHC experiments that are made out of 2 chips. They with large electrodes that have a larger capacitance and have typically the electronics inside the collection well, and with buried electrodes that have the advantage of now not having the backgate effect and have a smaller drift path. We're pursuing this program with the TowerJazz 180 nanometer CMOS technology. And as I will show you, we need some process modification for radiation hardness. So what is this TowerJazz 180 CMOS process? Well, we can produce pixel detectors that have 3 micrometer square collection electrodes with 5 femtofarad input capacitance, with small depletion depth up to 20 or from 20 micrometers, and with high signal to noise ratio starting at 20. The process modifications that I've been talking about is we had to modify the original Alpine design with a continuous N-layer blanket, which is the first one for full lateral depletion. We had to modify it, and then there was 2 additional modifications. One that we call the N-gap, or the gap in the N-layer, which is just the modification of the mask that we introduced. And there was a second modification, which is what we call the extra DP well implant, where it's an additional mask that adds some implants on the DP well. All these processes modifications can be found in these presentations that I list here, publications I list here. Now let me tell you a brief story about the R&D in radiation hard monolithic detectors. So we start in January 2018 with the Malta 1 and the second version of it, which was a large demonstrator with a synchronous readout with electrode, small electrode size and reset mechanism that we had to evaluate. That had very poor lateral field collection. Then we went on to a second design by January 2019, which was the Mini Malta, which was a small demonstrator and had full efficiency, as I will show you. Then after that, we go with Malta C, that was basically a substrate engineering by redoing the Malta design. And I will show you enlarged cluster size and improved time resolution. And what is coming later is what we call Malta 2, which is expected by October 2020, that has a smaller matrix and also substrate engineering. And this will be the baseline for the CERN EP R&D program, work package 1.2. Now let me come back to Malta. What is Malta? Is a full-size demonstrator 2x2 centimeters square that has more than 250,000 pixels, as you saw before for the ARCADIA, similar one. We have 8 sectors with different flavors and has a fully clockless matrix architecture, which means that we have an asynchronous readout all the time of 37 bits through a bus. Then this means that the digital power that we have is 10 milliwatts per square centimeter. If we look at the pixel design, which is 36 by 36 micron square, and the small electrode and the spacing, we are talking about an analog power which is of the level of a microwatt per pixel, and in total like 70 milliwatts per square centimeter of analog power, which I cannot tell you how advantageous that is for building a pixel detector. The Mini Malta design was a much smaller demonstrator that had only 64 by 16 pixels on the same size. It had 8 different sectors based on the Malta pixel front end. And here in this design, we implemented the N-gap and the extra DP well process modifications I will show you. And also we introduced larger capacitors in some of the pixels to address some RTS noise. So this slide is basically a summary that you probably have seen already that shows you the full matrix of the Mini Malta. And you can see how there's 2 sectors on the left that are using the enlarged transistors and have the N-gap. There's a sector with the N-gap at the top, and then second to the top here is the one with the extra DP well that show full efficiency after 110^15 neutral equivalent at 200 electron threshold and 6 volts bias. Okay, so this is an impressive result. And why is this so? What is good here is we improve the charge collection in the pixel corners with respect to the previous design. I'm not going to show you those results. I have also to mention that this was also validated or observed also at the focused X-ray beam at time on light source. Now, how does this go with threshold? So here you have a plot that you see efficiency is a function of the threshold. And immediately what you see is 2 trends. You can see the red and the orange that are the enlarged size transistors, and the bluish colors that are the standard size transistors. There's 2 different groups here. You see immediately that there's lower thresholds for the enlarged transistors, which is very good. And there's also higher efficiency for the enlarged transistors. We also see slightly higher efficiency for the additional process modifications that I explained, the N-gap and the extra DP well. But there's similar performance between having an epi thickness of 25 microns and 30 micron thickness. Okay, so these are the results, are very good. What are the effects that we see on TID up to 100 megarad? Well, if you look at the amplitude gain and the noise similar to the results that we saw for the ARCADIA, you see there's 2 different trends with the transistor size. You see the red curve, the red points and the blue points. There's higher gain for the enlarged transistors, and it's, I would say, more or less stable up to 100 megarad. And we also see that the noise increase for the enlarged transistors is smaller. So there's 20 electron noise compared to the 30 electron noise for the standard front-end size. Now, let me talk a bit about these Czochralski substrates. As I mentioned before, Malta was reprocessed on this high resistivity Czochralski substrate, which has a resistivity of around 800 ohm per centimeter. That allows us to have larger depletion voltage up to 50 volts and has an increased charge collection. Why did you do this? We want to aim for better time resolution and higher radiation hardness. And the samples that were reprocessed in the Czochralski substrate contain on the full matrix the different flavor modifications. So they contain either the continuous N layer, which we call the standard. They'll contain the N-gap or the extra DP well all around the matrix. This is a plot where you can see the current as function of voltage, where you can see we can actually operate these devices up to 50 volts. Now, what are the operational limits of these type of devices? Well, we can measure these operational limits by measuring the current between the P well and the sub as a function of the sub voltage, and the devices will be limited up to 20 milliamps by either punch through, which is the current flowing between the substrate and the P well, or the leakage current, which is the current flowing between the substrate, P well, and the collection electrode. So what you see on these devices is that they are all very well behaved, except, or very constantly uniformly behaved, in the sense, or except the Czochralski samples that were produced with the NGAP and the extra deep P well, that without irradiation are limited by punch through, and after irradiation are limited by leakage. So we expect some change in behavior in these samples compared to the other ones. Now let me talk a bit more about how do we do these measurements. So for instance, the test beam campaign we did at DESI October 2019, we used a custom Malta telescope for this, which uses a fast readout and online monitoring, and a cooling system. And you can see there's huge pipes that keep the sample at -20 degrees. So what is good here is we can trigger directly out of the Malta planes through a combination of the reference signals. And we can define, for instance, ROI on the tracking planes, and then we can check the hits on the DUT online. And this allows us very fast turnaround of data taking. A highlight of the results that I can show you from these test beams can be summarized here on the efficiency on the Malta samples on this Czochralski substrate, where you can see that we have almost full efficiency on the Malta on this matrix when we have the NGAP process modification and have been irradiated up to 10 to the 15 neutron equivalent, if we compare it to the unirradiated sample. So we have almost full efficiency. Now we're still working on what happens at the 2 times to the 15 neutron equivalent.
2 minutes remaining.
Thank you. Let me show you a couple more pictures. So one of them is the cluster size on the EPI versus Czochralski. So you can see that the Czochralski samples have a higher cluster size, like 1.8 cluster size compared to 1.2 on EPI, and 1.4 on the Czochralski NGAP. Now, what happens if you irradiate them? The Czochralski substrate with the standard process suffers from radiation damage. Okay, so this is very characteristic, which means that the NGAP has larger cluster size than the standard modified process, and it stays there. So the NGAP has better radiation tolerance. Now, how do we, a bit more on tracking resolution. Let me talk to you about we use the general broken lines algorithm for track reconstruction to mitigate scattering effects. And we can extract the telescope resolution from the convolution of a Gaussian with a two-sided step function, which has a pitch of Malta. And what we see is we can get a 10.5 micrometer resolution. Now, if we were to use the Czochralski samples for this thing, we can see that we can improve the tracking resolution of the telescope down to 6.1 micrometers by using these Czochralski samples at a higher bias. We can go for a tracking resolution of between 6, 20, or 30 volts down to 9, 7, or even 6 micrometers. So this is very good. Now, last plot, let me show you a bit on time resolution. So we can extract the time resolution through the linear combination of the planes in the Malta telescope. And we can see that there's a time resolution of 2.6 nanoseconds for the EPI, which can be compared to 1.7 nanoseconds if we use the Czochralski samples above 10 volts, which is due to the increased depletion voltage. And this, just as a reminder, we have an in-time collection efficiency or in one bunch crossing, which is close to 95% on the Czochralski samples. So let me conclude that the Malta monolithic CMOS sensor is a prototype that has been produced in 180 tower jazz technology, which has an interesting candidate for a small electron monolithic CMOS prototype for high luminosity LHC and beyond. These additional process modifications, like NGAP and the extra deep P well, have shown full efficiency after 1 to 15 neutron equivalent irradiation. And the substrate engineering, which we call this Czochralski substrates, have shown an increase in tracking and timing resolution due to the increased depletion depth and charge sharing. And I think it's worth mentioning that we will continue to explore this design in the context of the work package on development of monolithic CMOS sensors for the CERN EP R&D program. That's it. Thanks a lot.
Thank you, Carlos, for the plenty of results in your presentation. Does anybody have a question? I don't see any raising hand. Can you give a little bit of detail on the new chip which you expect later this year? What do you expect as the big challenge maybe, or new thing?
The new thing on this chip is we expect better control of this chip, which has been up to now very challenging. I mentioned we have to deal with a chip that is asynchronous, that sends the data continuously all the time, right? And this has shown to be a challenge if we cannot control the chip properly. So we have introduced changes in the control part, and we have also changed a bit the front end and the process modifications. It comes with 2 additional process modifications that we hope will allow us to handle better 2 10 to the 15 neutron equivalent and even higher. We are aiming at 5 10 to the 15, but this is a secret, don't tell anyone.
Thanks a lot. Then I would like to thank all speakers of this first part of our session. We have a 15-minute break. I invite all of you to stay connected. Maybe we have a virtual coffee. Just speak. We see if it will be a mess, I have to arrange somehow with raising hands. And yeah, so the floor is open for a 15-minute break. So we continue, or 10-minute break, we continue 10:15, so in a little bit more than 10 minutes. Maybe I have a very naive question. Peter Berta, our first speaker, maybe you can prove that your microphone is working, and
yes, hello.
Comment in which area of Europe or the world are you?
Hello, this is Peter. Can you hear me?
Yes.
Okay, good morning. Yeah, so it is a good idea to test the microphone. I am currently in Prague, in fact.
So you're the closest. Okay. Then I'm curious who is connected and thinks he's the furthest away.
Sorry?
This is Mike Foley. I'm in Massachusetts, near Boston.
Yeah, this is quite far away. And then we also had somebody from China, right? Yeah. From the organization team also, I would like to invite all of you for the poster session this afternoon. Michael, correct me, but I think it starts at 1:30. And we had yesterday, quite nice presentation of many posters and some discussion. So I invite you. Okay, Brian, sorry, Michael, you're quite far away and got up very early, right?
Well, yeah, I had to get up early for the first connection for 1:40 a.m. Yes, that was pretty early.
Yes. Okay.
Well, actually, it was late. I didn't go to bed.
Okay. I see. Peter, since we have time, maybe you also want to check the sharing quickly, then we can continue after the break easily.
Yes, exactly. I also can...
we see you even. Hi.
Yeah? Okay.
And then Qun Ouyang, you're in China, so I guess it's also far away, and for you already late afternoon. Okay, we don't know. Okay, we can see the presentation, Peter, very well.
Also full screen?
Yes, perfect.
Okay, very good.
Sorry, may I also take the occasion to test my setup, because I'm gonna present right after the pause. So I am Mattia Soldani, and if I am allowed to do so, I will try also to share my screen.
Yes, I was about to go through the other speakers exactly. So we can hear you well. Go ahead.
Sorry for anticipating.
No, go ahead. It's all good. Yeah, we can see the slides very nicely. Very good. And then you're in Italy, I guess.
Yeah, so I'm quite close.
Okay.
Not the closest, but yeah, thank you very much.
Yeah. Then I'm curious, Sen Quan, I cannot see you connected, at least not in the list. And Or are you hiding behind any other name which I misinterpret? Also, sorry for pronouncing maybe names wrongly. I see the slides are uploaded. Michelle, we didn't hear anything about Sen Qun, right? Felix Klipsner, maybe we also do with you the check quickly on audio and sharing. Maybe enjoying the break. Felix, can you confirm that you hear us and also speak? Then I see Giovanni Tassielli. Can you give a sign of a connection? No, he also left. Okay. Michelle, did we hear anything from Sen Qun? I did not see him earlier connected. I see slides are uploaded.
Yes. His slides are uploaded.
Yes. Okay. We will see.
Hopefully he will be here.
Yeah. Brian Hackett, I have a naive question. So you are about to upload, right?
Yes, I'll be uploading very shortly.
Thank you. And do I get correctly that the speaker before you is a different Brandon Hackett?
Yes, I
There's
saw
no
that.
typo. Good.
It's somebody different, yeah. It's interesting. They have such close names.
Yeah. Okay, thanks. May I ask, which part of the world are you?
I am in Washington State in the USA.
Okay, so you also didn't go to bed, or?
I went to sleep for about 2 hours.
Oh, thanks a lot for accommodating our virtual conference. And
so she wins the earlier version of me.
Yeah.
Yeah, it's currently 1 a.m.
Thanks. And your last, so you okay. Thanks a lot. Then we know, Beatrice, we saw earlier you're in the office somewhere, right?
Yes,
when we did the check.
Yes.
Yeah, so you have a good time zone. And let's see, Felix is maybe back. Then you can share your slide and say a word. Not yet. Okay. Yeah, in the beginning when we tried, we saw that there for some people a little bit the bandwidth is not so good, so we reduced the video usage. And it's nice if the speaker can show the video. Okay, we can move it. May I ask again if by now Sen Qun has connected? I see a few more new people connected. Okay, not yet. So Zach, you're also in the US, I guess. Okay.
Sorry, did you say Zach?
Yeah, that. You're also in the US,
yeah.
So you also
actually,
have a not so comfortable time.
No, I'm actually based in Geneva, so
okay.
I'm currently at CERN, well, virtually at CERN.
Yeah. Thanks. Michelle, yesterday it was mentioned that somebody presented from the beach, right? so hopefully not too noisy. Thank you, Brian. And before restarting, one more time, I'm asking to Felix Klitzner. Can you confirm you can share and also say a word? Okay, not yet. And for all new speakers joining, I will say 2 minutes. So you have 15 minutes, 12 for the oral presentation and 3 minutes for questions. And after 10 minutes, so 2 minutes before your presentation should finish, I will remind you and then ask all of you to keep the time. Since we still have a 2-hour session to go, a little bit more than 2-hour session. Peter, maybe you already prepare and start sharing, and then we start in a seconds.
Oh, okay. Good. So can you see my slides full screen?
Yes.
Good. Should I start?
Yeah, let's get started. Go ahead.
Okay.
And,
so good morning, everyone. I present you PyLab and underlying event mitigation with the so-called iterative constituent subtraction. So first I will have a few words about PyLab. Then I present you the previous older method, constituent subtraction, and then I present the new method, which is called iterative constituent subtraction. So PyLab are simultaneous proton-proton collisions in one bunch crossing. As you know, as we want always higher luminosity, higher instantaneous luminosity, we also get higher PyLab. For example, at LHC run 2, we get up to 70 interactions per bunch crossing, but this number is still too low. And in fact, in future, for example, for the higher luminosity LHC, we can expect up to 200 interactions per bunch crossing. So this PyLab is a problem. It has negative effect for jet reconstruction, for hadronic jet reconstruction, because PyLab randomly adds energy deposits to calorimeter. For example, 20 PyLab events adds roughly 50 GeV additional PT under a larger jet and DKT R equals to 1 jet. Or for example, the plot shows the jet mass distribution for larger jets containing the top quark. With black points, we can see this distribution without PyLab, so it is nicely centered around the top quark mass. But when we add 60 PyLab events, then this distribution is shifted to the right to higher values, and also it is smeared a lot. So PyLab is really a problem, and there is need to mitigate PyLab effects for jets. Here I list selection of PyLab mitigation methods. The most known is the so-called area subtraction, which was already used in roughly 600 physics measurements at the LHC. And the other method is called constituent subtraction, which is a newer one, and it has better performance than the area subtraction method. It was already used in 12 physics measurements. Then there are also other methods such as soft killer or PAPI. PAPI is used at the CMOS experiment. And then the newest topic of this talk is the iterative constituent subtraction. So I will talk about it later. Just a comment about heavy ion collisions. In heavy ion collisions, the underlying event has roughly the same negative effect as pileup in proton-proton collisions because it creates a soft background in the rapidity azimuth space, as is visible in this bottom right plot. And so very similar methods are needed to correct the underlying event in heavy ion collisions as for pileup corrections. Okay, so now a few words about the constituent subtraction. So this is the older method, which is, let's say, already well known. So just as a reminder, it is a pileup subtraction method at the level of inputs. It's the generalization of the area subtraction. It also exploits the background PT density, the so-called rho. This rho is roughly the amount of PT from pileup particles per unit area in the rapidity azimuth space. And there are two possibilities to use the older constituent subtraction. The first one is jet by jet, when we first cluster the jets, and then the jets are corrected individually. And the second usage is the so-called event-wide, where first the whole event is corrected and then follows jet clustering. In this second option, where first the correction of event is done, the jet clustering is less biased by the presence of pileup, so it is more preferred. On slide 10, then I list various measurements, so where the constituent subtraction method was used. So there are roughly 12 physics results where this constituent subtraction mitigated the effect of pileup or the effect of underlying event in heavy ion collisions. And as you can see, the various experiments use them: ALICE, ATLAS, CMS, and STAR. Okay, now I try to explain how the constituent subtraction method works, the event-wide version. The plot shows an example event only in the azimuth space, so only in one dimension, but the correction is done in 2 dimensions, in azimuth versus rapidity space. And with blue are the hard scatter particles, so they have typically larger PT and they are concentrated at certain phase space. And then with red are background particles from pileup or from underlying events. And they are soft particles distributed randomly in the event. So in the first step, the rho, the background PT density, is estimated. Then in the second step, ghosts are added to the whole event. These are these green, very low PT particles, as you can see in the plot. Then in the next step, the PT of the ghost is set to negative value corresponding to rho. So roughly to mimic the effect of pileup. And then in the next step, on slide 14, there is a matching done between the ghosts and the real particle. This matching algorithm is based on the distance delta R between particles and ghosts. And this procedure ends until the delta R is lower than certain free parameter. This free parameter is called delta R max. And at that point, the procedure stops. So yes, as you can see on the plot, certain amount of ghosts can still remain in the event when finite delta R max parameter is used. And these are not matched, and these remaining ghosts are then discussed later. Okay, so this was the standard event-wide constituent subtraction method, and now I will present the newest developments, and this is the iterative constituent subtraction method. which supersedes now the original constituent subtraction method. The main idea of this new method is the application of the event-wide constituent subtraction several times after each other. So after each constituent subtraction application, the remaining unsubtracted PT from the ghosts is again redistributed in the event, and for each iteration, the different constituent subtraction parameters can be used. So this new method is again implemented in the FastJet contrib project, and it can be used from there. So now I try to explain this new method again on this example event. So 2 iterations will be done in this example. Again, the first step is the estimation of rho, of the background PT density. Then follows, again, similarly as before, addition of ghosts to the whole event. The next step is setting ghost PT to negative value corresponding to rho. The fourth step is the first iteration, where the ghosts are matched to real particles. And the fifth step is the redistribution of remaining PT from the ghost. So now the PT of the ghost is smaller because part of their expected background PT is already corrected. And then in the sixth step, the second iteration follows, where again the ghosts are matched to particles, and again more pile up or more background particles are removed from the event. Okay, so this was roughly how the method works. Of course, not only background particles are subtracted, but also hard scatter particles. And then, so we evaluated the performance of this new method and compared to the older methods. And this is shown in this slide 24.
Just 2 minutes remaining.
Okay, thank you. So the left plot shows the PT bias as a function of a number of pileup events for NTKT R equals to 1 jet for higher PT jets from a sample of Z prime to TT bar. And we can see that without any correction, the pink circles, there is large bias. So with increasing NPU, if increasing number of pileup events, the PT is biased a lot. And then with various correction methods, this bias is removed. So the jet by jet constituent subtraction, the area subtraction, and the standard event-wide constituent subtraction, and then the iterative constituent subtraction method is compared. So this bias is removed for the PT, and then on the right plot, a similar plot with similar jets just for the PT resolution. And we can see now that this new method, this iterative constituent subtraction, has the best performance. It has the lowest smearing for the PT. And then on slide 25, a similar performance plot, but for jet mass of larger jets. And yeah, on the left side again, the bias of the mass is removed with various methods. The best maybe is the area subtraction, but also the iterative constituent subtraction performs very good. And then on the right side, we can see the resolution of the mass, and again, this iterative constituent subtraction performs the best, similarly as for the jet PT. Okay, so the last slide summary. So I reminded you the constituent subtraction method, which is a competitive pileup mitigation method already used for physics measurements. And then I presented you a new method, the iterative constituent subtraction, And it shows a large improvement in resolution, keeping the bias well controlled. And of course, the experiments are encouraged to test this new method. Thank you for your attention.
Thanks a lot, Peter. Is there any question? I'm curious, to which amount of pileup did you already try, or what do you think is the maximum?
Yes, we have tried up to 200 pileup events, which is the expected number of events for high lumi LHC. This plot goes up to 120 only, just to better visualize. But yeah, also at higher pileup, the method works similarly as for the values of 100 pileup events or something like that. So up to 200.
Ah, you tried up to 200, okay. Because we saw earlier in presentations that the detectors tracking detectors with up to 200. Or, yeah. Okay, thank you.
Yeah, so this method does not depend on tracking, just on calorimeters.
But there's still a high pileup in the event.
Yes. So this method can then help basically to the calorimeters.
Thanks a lot.
Thank you.
We go on with Sen-Kian. I see you now connected. So you will present on R&D of ultra-fast 8x8 readout MCP PMTs. Sorry. We can also hear you. Now please share the screen.
Yeah. Can you see my slide?
Yes, and in full screen. Yes.
Yeah, thank you very much. Give me a chance to report our result of the first MCP PMT research and development MCN from IHAP. And my slide could be divided into 4 parts. First, the motivation and some simulation work, and also the evaluation method for how did we test the FPMTs. And the last one is the last part is some prototypes for the FPMTs. First, this slide shows why we want to produce the 2-inch fast MCP PMT. We can see that this is the diode part, because every expert here familiar with the diode part. This is the 2-inch MCP, 2-inch PMTs with diode part, and also this 20-inch PMTs from Hanwha. So this is, we call this smaller PMT, and this is a large PMT. Now we are the group in China. We have a cooperation group with the institute and the university, and also some faculty together. We have already successfully produced the 20-inch MCP PMTs, and sometimes some of us was free, and we just think about it is possible we can also produce the 2-inch MCP PMT as the photonics and the phototech or HMS with the MCP modules. By this way, so we designed the 2-inch fast MCP PMT with the, we want to produce a high QE and also with the low cost. And this is the ability why we want to produce the 2-inch PMT, because we have already successfully from the 2009 we have a design and produced the 2-inch MCP PMT and 5-inch and 8-inch, and finally 2015 we have already produced the 20-inch MCP PMT, and then we have 4 years to mass production this type of PMTs. And nowadays we have already produced the 50 kilo pieces successfully used in the Juno, the neutrino observation on the ground in China. And we have the core technology for the PMTs, such as the high QE photocathode, the high gain and low cost, low noise MCP modules, and also the low reductive glass and the vacuum transfer equipment. So this is the date of the large PMTs, and also we have the aims. We want to produce the fast PMT, for example. The QE should be the 30%, and the anode at least 8 times 8. And the read time, it must be less than 100 picosecond, and the GTS of the single photo spectra should be the filter picosecond as a gain should be 10 to 7, and the dark rate was much low with 100 millimeter square, and the cost should be low because if it is too expensive, and maybe a little people could use it. And the roadmap of this design for the FPMT could be into five parts. You can see the high QE photocathode and the low noise MCP modules, and the sealing, because we need the glass and the MCP and the crosstalk free anode part together by the sealing part to keep the vacuum. And also the last time we need the high density electronics. It's very important for the high picosecond temperature solution. So we have the design and we want to produce the prototype from the similar ones, simple one, from 1 inch, 2 inch, also the 1 inch with 4 readout, and then the 2-inch square part with 16 channels, and the last one is the 64 channels in the 2-inch. This is our roadmap. And also we have some simulation work to do this. And yeah, you can see that this is the why not? Yeah. You can see that the electron coming to the channels and then be amplified a lot, just like this. This is the angle distribution. By this simulation work, we can get the angle distribution about the MCPs and the TTS and the anode resolution and the gain and also the raise time of the output signals. By this way, yeah, this is the full screen. Yeah. By this simulation work, we first we have confirmed this data to the experiment data. It should be correct. For example, we have put one simple FPMT prototype with 1 channel readout into the magnetic field to test the anti-magnetic field performance. This is the test result from the simple. This is the simulation models for this. We can see that when the amplitude reduced to 100%, and the anti-magnetic field was the 5 Tesla, and the simulation work was found 5.2 Tesla. That means the data and the simulation data was correct. So with the correct simulation models, we can do some correct design for the new construction of different types of MCP PMTs. For example, we know that usually the PMTs was coupled with 2 MCP modules. The TTS simulation work was the best one is 10 picosecond and the read time about 85 picosecond. And we can simulate with the same gain. And if there is only 1 MCP module, we can see that the TTS was only 4 picosecond, and the annual resolution and the read time were much better than the 2 MCP modules one. So if by this way, if we have the fast amplifier for this 1 MCP module, when the gain was achieved 10 to 6, it will be easier to test the single PE. But you know, it is very difficult for the 10 times faster amplifier. But this module could be used in very large photo detectors, because with the number of photos large, the gain is okay to detect the signals. And after the simulation, we have the lab to test the fast PMTs. We have with the picosecond laser to generate to operate this PMT with its works. This is gamma to generate the photoelectron and then amplified by the signals. And also the photocathode could be, this is the noise. We have the TDC modules to test this start time and stop time. This is the Seyedali's signals to be the stop time, and the signals of the PMTs to the start time. This is get the TT and get the sigma of TT was the TTS. And also we can use the oscillograph to test the NIM signals to have the stop signal and the plus signal to do the start time. We can also get the TTS. By this we tested some prototypes in our lab. Some of the prototype was produced by our groups, and some was produced by other company in China, and this is the BMP in Russia. We have already tested them. We know that the TTS will have the relationship with the number of the photos, and with the number of photos increase, and the TTS will decrease a lot, but there is should be the plant. We call this is time-limited TTS. Because some of the modules cannot test the TTS of the single P, but every module could be tested the TTS in the limited. So we can use this limited TTS to report the performance of the FPMTs in the later. So why? Because we want to use this data because at the beginning, we produced some prototypes. For example, this is a 1-inch with one channel prototype. Some of them could, with the quantum efficiency, was about 17%. Some of them good single P. The peak-to value was about 7, but some of them cannot test the single P. So we can see that the best typical single P of the TTS about 20 picosecond, 200 picosecond is large, not our aims. We need to improve a lot. Also, the read time was not good, but the limited TTS was only about 25 picosecond. That means it's the MCP modules is good, but the readout electronics and maybe some problem, we need to improve it. That's why we have we did another prototypes later. And this is 6 channels readout PMT prototypes. We can see that this is the square part, and the anode was 16 channels, and this is the high voltage versus the gain. And when the gain was enough, when it was about 100 less than 1700 voltage, the gain was be at 10⁻⁷, and this is the signal was beautiful, but this is the reference part. And the read time about this about 250 picosecond, because we use this connector to test this signal. Some electronics will have problem. If we test the signals from this MPMT directly, the read time should be much better than this one. And we can see that the peak-to value of the single PE was about larger than 2. And the 16 channels, every of the channels could test the single PE, and the gain have the relation. The gain was the uniformity of the gain was good. And the TTS about the single PE, this one channel was about 100 picosecond. It's much better than the one channel PMT's prototypes, but it still needs to improve for us. And also the TTS limited TTS about 28 picosecond. That means we use this the same type of MCP modules produced by our corporation companies, and the constructor as we have designed, the limited TTS was put less than 30 picosecond, but we still need to improve it. And last week,
remaining.
Okay. Last week we just get the 64 channels readout PMTs, but unfortunately, the read time was not good, and also it cannot test the single PE. The TTS limited was about 30 picosecond. The reason because the convenience variance of nowadays, and it's delayed our prototypes in the factory. But we tried our best to produce the 8 times 8 64 PMTs in the later. We hope in the maybe 2 or 6 months later we can get the 64 channels readout PMTs to test. That's all. Thank you very much.
Thank you very much for your presentation.
Yeah.
Are there questions? So with the new PM 8x8, which you just received, what is the most challenging measurement? What do you expect to do?
Yeah, the most challenge for us was the sealing. We wasted a lot of time because we have the ability to produce the larger one, but for the smaller one, it's really difficult. And we waste a lot of time to sealing this to keep the vacuum. And nowadays we successfully keep the vacuum, and then we need to improve the MCP module and the photocathode. Then we'll be test good single PE for the TTS.
Thank you. And thank you for your presentation. And we move on with Felix Klitzner on a novel two-dimensional readout design for floating strip micromega detectors.
Yes, can you hear me?
Yes.
Okay.
And can you stop sharing?
Yeah, okay, stop it. Thank you very much.
Yes, thank you.
Thank you.
Okay, one moment. Okay, can you see it?
Yeah, very well. And
all right, okay. Some full screen. I think it is here. No, where is it?
yeah, I think
I cannot see it.
yeah, this
Like this one. Ah, yeah, no, okay. Okay, shall I start?
Yeah, please go ahead. We can hear and see very well.
Okay, so good morning, everyone. I will talk about a novel two-dimensional readout design for floating strip micrometer gas detectors. So this is the table of contents, which I will just skip for the moment. Jumping directly into the functional principle of micrometer gas detectors. So these are so-called micromesh gaseous detectors, which feature two different regions, which are separated by a thin woven micromesh, which you can see here. So above the micromesh, we have the so-called drift region, which is collecting the ionization charge. In this case, the electrons are following the field lines, moving through the holes of the micromesh into the amplification region. So the drift region is typically a few millimeters wide, so 5 to 6 millimeters, and the amplification region around 100 microns. So after the amplification, the signal is collected on the anode. In the case of floating strip micrometer gas detectors, the anode consists out of copper strips, which are individually connected to high voltage via high ohmic resistors. So they are kept on a slightly floating electric potential, which is why the reason they are called floating strips. For the readout of the signals, then we use copper readout strips, which are congruent to the floating strips, usually separated by a thin insulator. In case of discharges, which can happen in micropattern gaseous detectors, only a few strips are affected, so 1 to 3 strips, and these are usually very fast recovered. So the detector is intrinsically very high rate capable. The question now is it possible to design a two-dimensional readout with another perpendicular layer of readout strips? So that is what we investigated. For this, we set up a ANSYS simulation where 3 copper strip layer anode has been assigned. The geometry you can see on the left of the amplification region. So you see the mesh here, and the gas volumes in green. The floating strip FS is here. Then we have the insulator in yellow. Then directly above, below the floating strip, we have the perpendicular readout strip, which is called Y strip from now on. And then below the Y strip, we have the parallel X strip. For all the simulations and measurements I'm going to show you, we usually used a strip pitch of 0.5 millimeters. Then we use ANSYS to calculate the electric field configuration in the detector. So the solution for setting the floating strips, for example, at 580 volts, you see on the right here. And then we can just export the electric field and import it into the Garfield++, where we then do the charge, carrier drift, and amplification. Here you see, for example, in yellow, the avalanches of the electrons, and in the grayish color, you see the ions, which are moving towards the mesh. The question is now, what kind of signals are we expected to see on the readout strips? Essentially on the Y strip and on the X strips here. And the answer to that is it is a combination of directly induced signals and capacitively coupled signals. So first of all, I will talk about the induced signals by the charge movement in the amplification region. And these signals are induced on electrons, as I said, by the movement of charges through so-called weighting fields. You can calculate it via the Shockley-Rameau theorem, which is shown here. I will not go into detail, but what you have to know is that the sign of the current which is induced on an electrode, for example, on the floating strip here, is not only depending on the sign of the charge, but is also depending on the, let's say, on the scalar product of the weighting field with the movement of the charge, which means in case of the floating strip, you see the signal which is induced here. It is a fully negative unipolar signals, which is divided into the signal from the electrons and from the ions. And it is purely negative because the weighting field is always either parallel or anti-parallel to the movement of the electrons or the ions. Now, if we look at the perpendicular strip, which is the Y strip here, you see that we have a positive bipolar signal. And that is directly the consequence from, let's say, the weighting field lines, which have different directions. So they are either bending to the floating strips or they are bending on the field lines, depending on the position of the particle itself. So for the electron avalanche, where most of the charge is created very close to the floating strip, most of the electrons see, let's say, a parallel weighting field line to their movement, which means the signal which is induced is purely positive. Then if the ions move towards the micromesh, the signal is initially positive because it is anti-parallel, and then at some point, roughly at half the amplification gap, it gets negative because it is parallel, sorry. Okay, then the signal on the X strip itself is suppressed by around 3 orders of magnitude because essentially the weighting field lines are shielded by the perpendicular strip, which is directly above. However, we did not include the capacitive coupling between the floating strips and the readout strips. That is what you can see here. So we simulated the capacitances with ANSYS and calculated the charge sharing. Here you can see the signal as a function of the time. Again, left for the X strip, right for the Y strip. And what you immediately see is that for the X strip, the dominant signal is the capacitively coupled signal from the floating strip, which is the green line here, which is almost the black line. And for the Y strip, we see the dominant signal is the blue line, which is the directly induced signal. So we have two different mechanisms how the electrodes receive their charges. To find out how much charge is actually induced on the two readout strips, we just integrated the current and see in this case that for this particular strip geometry, we only see around 5% of the total charge which is created in the avalanche is coupled to the readout strips. So we clearly need an optimization of the strip geometry. But first of all, what we also did is we stimulated the front-end response of charge-sensitive preamplifiers or a shaping network, which in our case, we used the APV25 hybrid board. So we calculated the delta pulse response, the transfer function, and then convoluted the current signals, which we found from the simulation with the transfer function, and compared it to a measurement. That is what you can see on the bottom here. So on the left side, the response of the X strip, and on the right side for the Y strip. And you see the simulation as well as the measurement is in very good agreement. So we do understand what is happening inside the detector. And now we can optimize the anode to increase the yield. And that's what we did. So on the left side, you see the classical designs. So classical in this case means that they are really only straight strips in the detector. So essentially the perpendicular strip, what you see here. On the right side, we have the novel designs where we change the width of the perpendicular strip according to the position. So, sorry, if the strip is below the floating strip, we want it to be as thin as possible because the two signals are of opposite polarity and we do not have very good capacitive coupling to the strip. So we want to reduce this. On the other hand, we want to be as wide as possible between the floating strips because we want to see the directly induced signals. And the second thing is what we did is we removed the width of the floating strip as the floating strip essentially shield also the directly induced signals on the perpendicular strip. So this increases the pulse height on the perpendicular strip, but also on the X strip because we have now a bigger overlap between the floating strip and the parallel strip. And that is what you can see here if we did the comparison measurements with the classical and the novel designs. So we used an iron 55 source for the comparison measurements in a humidity and temperature controlled environment. And the results you can see basically here. So this is the average signal, so charge as a function of time on the strip with the highest charge, left X layer, right Y layer. And what you see is that we have a considerable increase in pulse height on both readout strip layers, which is very nice. Then we also wanted to test the spatial resolution and the efficiency in high energy beams of the detector. That's why we went to CERN with an external track reference system. In this case, we used so-called TMM chambers, which are resistive type micromegas detectors with two-dimensional position resolution. And we can then extrapolate the track into our floating strip micromegas detectors and check the spatial resolution and efficiency. We did it for perpendicular tracks, for inclined tracks, and also for perpendicular tracks at high rate. Here you see the results for the perpendicular tracks. Basically two residual distributions. On the left, the X layer, on the right, the Y layer. We fit those two distributions with a double Gaussian function to extract the spatial resolution. If you then weight the two integrals correspondingly, you end up with a spatial resolution around 80 micrometers for the X layer and around 50 micrometers for the Y layer, which is very nice. But you also do see that the X layer spatial resolution is a little worse than the Y layer resolution, which is because the charge cloud in the drift region is on the same size as the floating strip pitch, which leads to charge discretization effects and thus degrades the spatial resolution on the X layer. If we count the good events, let's say the tracks inside a 5 sigma window of these 2 histograms, we end up with around an efficiency of 98%, which is very nice. Now coming to inclined tracks. For inclined tracks, we do not usually use the so-called centroid method, which is based on the charge which is deposited on the anode, because of the charge clustering of the track or along a track which is traversing the detector. But we use a so-called micro-TPC method, which is using the timing information instead. And this is usually a better approach. And here you see the results. So the spatial resolution.
2 minutes remaining.
Yes, thanks. Here you see the spatial resolution as a function of the inclination angle. So as you see for perpendicular tracks, we are well below 100 micrometers. Then if we increase the inclination angle of the particle, the centroid resolution essentially follows the expectation from the simulation just because of the charge clustering. And for the micro-TPC method, you see both layers are essentially the same and stay below 150 micrometers roughly at 40 degrees incidence. For a dedicated choice of drift and amplification fields, you also reach efficiencies above 97% for all angles. Okay, then we also performed high rate measurements with the pion beams. So we ramped up the beam flux up to 4.7 megahertz per square centimeter. This is an event display, what you see here, I think for the Y layer. And you see clearly multiple particles in the detector at the same time. So this is the time here, this is the strip number, and that is the charge. And this is clearly resolvable in both dimensions. So if you now check for the different parameters like the pulse height, the spatial resolution, or the efficiency as a function of the beam flux, you see it is almost constant up to 5 megahertz per square centimeter, which is very nice. The last measurement, what we did was a neutron measurements with a boron-10 coated cathode. The cathode you can see on the bottom here. Well, first of all, neutrons perform a capture process at the boron-10 cathode, which is then producing a very densely ionizing nuclei, so lithium and helium, which make a lot of charge in the ionization regions on the drift region, which means we only require very low gain. However, we wanted to check if the detector is still stable if we ramp up the values to MIP gain values, so a very higher voltage, which means 570 instead of 450, and we saw still the detector is performing very well. Additionally, as a nice side feature, we taped the boron-coated cathode with copper tape to see if we really reconstruct neutrons. Because what you would assume is that these densely ionizing nuclei will just be stuck in the foil, and you will not be able to reconstruct them on the anode. And that is what you can see here on the right. So the hit distributions on the left side for the centroid method, and on the right side for the micro-TPC, extrapolated at the cathode, because this is the point of origin of the nuclei, and you see that you have a better spatial resolution for the micro-TPC than for the centroid. And yeah, I think that's basically it. I'll leave this slide for you. Any questions?
Thanks a lot. May I repeat the other questions? I can just encourage people to ask, raise their hand and ask. Maybe you can comment a little bit on how difficult those new novel chambers are then to produce. Because I guess you would like to have some application at some point.
Yes. Well, essentially, we did the production of these chambers really at an industry and a PCB manufacturing company. So this is, once you have the design, it is not really difficult to produce them.
Okay, thank you. I see Benedikt, you have a question. Go ahead.
Yes, just I think simple question. Why did you decide to fit a double Gaussian for the resolution?
Well, usually you have two, let's say, kind of events, which is the one place you have, let's say, the ionization charge, which is created along the track and drifts down. But sometimes you have, let's say, delta electrons which are created, which are, let's say, shifting the reconstructed position of the particle, let's say, which you can cover with the second Gaussian typically, and then you can say, okay, so this is, let's say, the resolution for really no delta electrons, and then you have the combined resolution of the detector.
Ah, okay. So because if you are perpendicular, these delta electrons, they will just shift your centroid somewhere else, so you get
exactly.
Yes. Okay, and in this, if you have these inclined tracks, can you actually separate delta electrons from the track? Because, for example, using some half-line fit or some
Exactly. So yes, so usually for the micro TPC, of course, you want to perform a linear fit, a line fit, but well, if you then cut on maybe for the chi-square of the track and see that it's not very good, then you can perform a half transformation, find outliers, and perform the line fit again. So this is very robust, actually.
Okay, can I just have a last short question to this? If you have resolution with your tracking system, just the slide 11, I think you're right that the accuracy is 30 micrometers from your reference.
Mm-hmm.
So in fact, the resolution you show on the next slide is kind of the convolution of this 30 micrometers with the convolution of your system, right?
Exactly, yes.
So in fact, you are kind of better than this 70.
Yeah, you see. I mean, this is not yet corrected for the track accuracy, this histogram. So this is really the exclusive residual distribution. And if you then want to calculate the spatial resolution, which is here, where I did the convolution, the unconvolution, let's say, of the track accuracy, then you end up not at 70 microns, but at 79 microns after that. Not only weighted, but also deconvoluted the track accuracy.
Okay, thank you very much.
Sure.
George, you have another question. Please go ahead.
Yes, this is George. Hi, Felix.
Hi.
Very nice work. I just had. Can you go to the slide where you say the high rate?
Yes.
The high rate. Just out of, I mean, I was just thinking, with the 5 megahertz, around 5 megahertz, when you're trying to reconstruct the track with perpendicular X and Y strips, you do have fake
yes.
kits. So I guess that this is not included here. So what you have 4.5 is an average particle rate and not just equally spaced particles. Is that correct?
Well, let's say the beam spot in this measurements was very, very small.
Mm-hmm.
So I think 2 or 3 millimeters in width, which makes, let's say, which boosts up the flux, so the rate per area to this value. Yeah, which means that not the detector is fully covered with particles, but let's say most of the time there's only 1 or 2 particles in the detector because it's a very small beam spot.
Mm-hmm. So you don't account for the fakes that you will reconstruct.
Yes, I do account. So I mean, the analysis, I also perform track finding and trying to find the best possible track.
Okay. Because I would imagine if you just irradiate the detector with such particle rate, you will end up with a fake
a lot of fakes,
particle refraction that you cannot really distinguish between 90 degrees. Yeah. Okay, thank you.
Sure.
Felix, thanks a lot for the presentation, and also thanks for more questions. I propose we go on with Michael Foley on the production of large area picosecond photodetectors and hear a status update. So Michael, you can exactly, we see your screen is there. Yeah.
Can you hear me now?
Yes. And maybe you go to full screen. And
I will. I'm going to presentation mode. How's that?
Very good. Go ahead.
Okay. You did the introduction. I just want to thank my collaborators, both at INCOM, University of Chicago, and Dragonfly Devices. The outline of the talk is, for an LAPPD, what is the detector? Where can it be used? And how does this work? I'd like to share our latest performance data. Since we moved from a couple of years ago when I gave the same presentation of prototypes, we're now in the production mode. So we have some nice consistent data here. I'd also like to share with everybody here some of our recent device developments, which include a capacitively coupled LAPPD, as well as a forward-looking smaller 10 centimeter detector, either in high rate or a high rate of detector. Also, right now we have a lot of LAPPDs that are available. I want to talk about our current applications, the collaborations we have, and then wrap it all up. So what is a LAPPD? It's essentially a large microchannel plate photomultiplier. And I use the word large because this thing is 200 by 200 millimeters square. It has an active area. If you take away the area by the X's, we're about 350 centimeters squared, or about 92% open area. And we're working to still minimize that. High gain is 10 to the 6th or higher. We are in the UV sensitive bialkali photocathode. We're typically in the mid 20s to 30% QE. We have exceeded that at a wavelength of 365. Position resolution, as you can see there, 3 by 3 or better. Time resolution, 50 picoseconds or better. And this is great for both single and multiple photoelectron events, but also in other applications where you see a penetrating energetic particles, such as time of flight or particle ID. And a great example of that is where we have multiple LAPPDs set up at Fermilab, and we're measuring events where the particles are going right through both detectors, and we can look at time of flight and actually look at the energies of those. Where can these be used? I mean, shrink-off light is a key event to be able to pick up, and with that, we need a device that has both high gain and fast timing. I mean, you're looking at a very, very tiny event. And if we can pick up that event, we can not only tell when it occurred, but where it occurs. And it's such a small event. I mean, you do get a lot of scintillation light afterwards from the volume, but in this case, with a detector that has a large area, fast timing, high gain, it can pick that up. And some of the applications range throughout high energy physics, nuclear physics, and in the medical community, such as Dune. We've heard talks on Dune. We've heard talk on Annie earlier, or in other sessions. Earlier today, I heard a talk on EIC, and that's a huge one coming up forward. A area that's probably not mentioned much in this conference, but is in the medical imaging, PET imaging, and proton therapy. Are two huge potentials for this device. How does this thing work? Well, essentially, I look at this, you look at it as an automobile. So you have a nice package around it. So we have a glass body that contains some strip lines on the bottom that's contained down here. You have a window, a window with a photosensitive coating on the inside of that. But the engine of this whole device are the two microchannel plates set up between spacers and in a chevron configuration. In our design, it's independently, the voltages are independently applied to the photocathode and each of the MCPs. This is creating the effect, and you've seen this in the talks before, but you have an incoming photon, comes down, you emit an electron, you get the shower through the first one, and then with the potential, it brings it all down, and then you pick up the avalanche or the cloud on the bottom, and that's measured through the anode for the strip lines that are coming on either side. And this kind of just gives you like the physical size of the device. Couple of key things here is we can independently apply the voltages. We have no wall or anode penetrations, and again the high area. A quick word about the MCPs. Again, these are 203 millimeter by 203 millimeter squares. The way we make these things in-house here is a process that can only make this size MCP. So we take a glass capillary array, we apply atomic layer deposition coating, and turn it into an MCP. Illustrated on the top right here is a cross section of one of these glass capillary arrays where we put down a resistive layer on top of the glass, a secondary emissive layer on top of that, electrodes on the top and bottom, and once the potential is applied, and you have enough energy of an electron to hit this, you produce a lot of secondary electrons, and this cascades all the way through the thing. So this is key, and shown here in the middle is one of our scientists showing how how large this device actually is. So first and foremost, one of the performance data here is our photocathode quantum efficiency and uniformity, shown in the color plots here on the top left and bottom left and the top right. We're looking at quantum efficiencies in the 27, 28, 28% QE. In the bottom center, you see the uniformity on this histogram, where it's a very, very tight distribution here, so very nice uniformity. And if you look on the bottom right, you see a cross-section or a scale of wavelength. So we, depending on the type of window we put on the thing, if we put a fused silica window on the top, we can actually get measurements down into the far UV, down to 200 nanometers. If we're using just a normal Boro flow window, oops, sorry about that, we can still get into, go back one, we can still get into, the typically in the high 300s. The other performance characteristics you want to look at are gain and dark count. On the top right, you see very nice pulse height distributions. These are well separated from the threshold here. The top left actually represents a capacitively coupled device, which I'll talk a little bit more later. The top right is a regular strip line LAPPD. Down at the bottom, we look at the dark rates. These dark rates are somewhere in the 10 to the 3 per centimeter squared. And this is, at an applied voltage, if we have a gain in the mid 10 to the 6th, say the voltage, photocathode voltage is about 250. And on the right-hand side, that shows some of the gains here. And on the left-hand side, we see some of the dark rates. So it's a very, very quiet type of device. Timing-wise, so timing, we have a few plots here on the right. So we have on the top left is a multiple photoelectron distribution measured on one of our capacitively coupled devices. The other three are all on our internal strip lines. And so we're looking at 46, 62 picoseconds, 52 picoseconds, and in the low 70s. Well, what we're seeing here is on 3 of them, we see a tail. And the tail is actually from some of the electrons will actually hit some of the walls around the pore channel. And they'll bounce back and then go through. And so you have this little tail of a curve. But on the multiple PE event, you're having so many of the electrons come through. And so you actually don't see the tail because you're flooded enough with enough events coming through. A couple of the key things to see here is the signal to noise ratio or gain really affects the transit time. So the lower the gain, the higher the transit time spread. The same thing with the photocathode voltage. If the photocathode voltage is too low, you're not going to get enough energetic photon or electrons going through and bouncing off, creating the secondary ones. So you want to have a good, find a good sweet spot for the detector to work at with the photocathode voltage and enough voltage on the MCPs to run that. 2 other factors I won't go into detail, but are the bias angle on the chevron pair and the diameter. Position, we measure position along a strip, shown here in the top middle, and a cross strip by centroiding. And by looking at the time difference between one end and the other, on the strip lines or centroiding across here, we're looking at uncertainties in the 1.4 millimeters across the strip, 0.76 millimeters. I mean, this is along a strip and 0.76 across the strip. Gen 2, this is one of our difference between the strip line and the one on the left and the capacitively coupled, where we actually put the internal ground plane on the inside. A key thing on the Gen 2 capacitively coupled is you can have a customizable anode pattern on the bottom for the signal pickup board, and this is based on the user's definition of what they need to use for their particular application. So a lot of flexibility. You can balance the number of pad with the electronics that you need, which is also a huge cost. But both of them are optimized for timing. This kind of shows a real live version of that, where the resistive anode is is applied on the inside of the package, the sealed LAPPD. On the top right here, we have the board with this. The photocathode is independent of the type of Gen 2, but again, the pixelated anodes, one key thing is this enables a high fluence application, and you could range the size of these pixels. We've tested them down to 3 millimeters square up to, in this case, that's 25 millimeters square. The capacitive couple preserves the rise time with capacitive versus direct, and that's key for timing. We also see we don't see very much degradation in the pulse amplitude, and that's also a function of the pad size as well.
1 minute remaining.
Okay, very good. I just want to make mention of a 10 centimeter device, and this one is to take advantage of smaller pore size MCPs for timing and B field, and then also being able to reduce the gap between the MCPs and the photocathode, and that's good for spatial resolution. We've tested these things up to about 1.5 Tesla. On the right here are some of the different schemes that we can do for this design. I do want to point out we are in full production right now, even called pilot production. So in 2020, we're doubling our output from last year, from producing 4 LAPPDs a month. Later this year, we'll go to 6. Our prototypes and our full-style baseline models are available for purchase or rent. And rent, these are renewable. We look for qualified prospects. They may not have the budget to purchase one of these offhand. We do have quarterly measurement and test workshops, COVID notwithstanding. But I mean, there's a number of advantages to do this, and this is at no charge for attendance. You just get there. We'll take care of feeding you guys and getting you familiar with it, but you say you have to get there. This, I won't go through this whole thing, but everything in red we've already delivered LAPPDs to. The rest we either are talking with them or we have pending sales in all these different applications, and they're ATP, NP, medical, and others. So in summary, some of the key takeaways are, we have our gain is 10 to the 6 and above. Our dark rates are pretty low. Our transit time to spread is 55 picoseconds or better. We have good QE. Our LAPPDs are available in 2 types of models, the strip line or the capacitively coupled. Again, this interchangeable, usually changeable pixelated signal board is key. The feature model we talked about. We have several ongoing tests with collaborators, more on the way. And again, we talked about volume pricing, monthly rentals, and income. We have all the technical support. I'm not a physicist, but we have the measurement and test team available. We have our workshops. And again, the curves on the left are just a summary of the different good features that we've seen. And I'd be remiss if I didn't wholeheartedly thank, the Department of Energy, Michelle Shin in nuclear physics, and Helen Marcisco and others in HEP. And we have several grants that have helped fund the research and get us into the commercialization where we're at. Thank you very much.
Thank you, Michael. Is there a very short, quick question? Then I propose looking at the time to move on. So thanks, Michael. And we will have next Gianfranco Tassielli, and with a proposal of a drift chamber for the IDEA experiment for a future E+ E- collider. You can see your slides just to full screen, maybe.
Now, come on. Okay, can you see my slide?
It's coming. 1 second, we can already hear you well. Okay. You're still in the presenter mode that we see 3 screens, or the main screen with the presentation and also the successor.
Oh, come on, I don't know why. Oh. I don't know why he's doing that. Okay, let's try with the PDF, probably it's better. Can you see it?
Yes, very well. So
okay.
Please go ahead.
Sorry. Okay, so I will present just the proposal for a drift chamber to be used like a central tracking detector for IDEA concept for future colliders. So that's if you want to learn more about the full detector, just see this Franco Bedeschi talk at this conference. So the outline of my talk, we just talk very briefly about what is FCCEE, so some specification about the tracking requirement, and then I will move about the IDEA tracking system and the drift chamber, and then something about expected performance and R&D. What is FCCEE? Is a proposal for very high luminosity circular electron collider that with the main aim to study very well the properties of zeta W, top quark, and Higgs boson. It will it is designed to have a very high luminosity in the range from 10 to the 34, that goes from 10 to 100 at function of the energy of what the beam will be. And just let me point out that when this accelerator will run at the energy of the Z, there will be a bunch crossing every almost 20 nanoseconds. So which are the requirements for a tracking system? So will be very, let's say, state-of-art resolution on all the momentum range of interest that are driven from, let's say, from the decay of the G and the H, and the fact that due to reduce the emittance of the accelerator, the magnetic field should be constrained to be of the order of 2 Tesla. And other aspect could be to have a good particle ID capability, and then will be some constraint about excellent BNC tagging and let's say small pitch. So having a good resolution impact parameter, this let's say almost drive the vertex resolution. And as I told before, there is a requirement to work at 100 kilohertz, so interaction at the pole. The layout of the full, let's say, tracking system for the detector, starting from the inner part, so the close to the interaction point, there are some layers, 3 layers of silicon detector, very light and very precise. After there will be a tracker, outer silicon tracker, very close to the drift chamber. There are some outer tracker in the forward region. After there is the central part of the drift chamber, this that go from, let's say, 30 centimeter up to 2 meter, and is long, say 4 meter long drift chamber, is a helium-based drift chamber. And after the drift chamber, there is another silicon detector just to improve the resolution in the, let's say, asymptotic limit. And then there is a very light solenoid that work at 2 Tesla that include everything. With this configuration, the full tracking system will have, let's say, amount of mass that is less of 5% of in radiation length overall, let's say, the barrel region, and less than 50% in the forward region. How it is, let's say, this is the sensitive, the sensible part of the drift chamber. So the drift chamber will have some square drift cell made with wires in a full stereo configuration. And we will use an approach, let's say, to how to construct chamber with very dense wire, using this approach, having 2 stereo view that then are squeezed together to be very close and create a unique, let's say, structure with a better, let's say, field wire to sense wire ratio. And in the total will be, let's say, 50,000 sense cell and in total almost 350,000 wires. The construction is inspired by the MEG2 drift chamber, MEG2 in experiment. So you can find some reference here, experiment for mu gamma conversion. And okay, why we think that the construction that we develop for MEG2 drift chamber is important for the drift chamber? Let's say we introduce 2 main features. Let's say to build a very light drift chamber, there is the first trick is So try to divide, respect to a traditional way to build a drift chamber, to divide the function of gas containment from the function of wire anchoring system, wire supporting. So if you can, so in this way, if you can construct two very specialized structures that are very light with respect to having, let's say, a full end plate that has to maintain all the gas and wires. In this construction scheme, you can create, let's say, the amount of material in the parallel reduced at the level of 10 to the minus 3 radiation length, and the forward goes to the 10 to the minus 2. You can see, let's say, since you have to put a lot of wire and very delicate wire, you have to try to have a different technique we will see after, but just in the picture in the bottom, you can see the magnitude chamber when I was assembled just before the closing, and on the plot on the left, right, you can see details about how the wire are anchored. So they are not going through fit through, but they are soldered on some special PCB. So this is why, this is some details. So as I told, it is impossible to build a chamber with a lot of wires, and in the case of MEC2, if they are very dense, because in the MEC2 the cell dimension was very small, in a traditional way, so putting wire one wire by wire, but you have to change the approach. The approach was having some PCB, using some specialized wiring robot, you can solder a set of wires, in this case of MEC2, TT2 wires, on a PCB, and then you have a support structure. In the case of MEC2 is very solid, but in the case of AD it will be very light. And then after you, the construction of the chamber is very simple. You have to put this PCB with a wire, then after you have to put a spacer, as a plastic spacer, and after another PCB with other wires. So stacking this structure, you construct very easily the drift chamber. And the fact that you're using a wire robot, you can reach a very high precision in positioning a wire and tensioning the wire. These are very crucial for the electrostatic stability of the chamber. Another aspect that is peculiar of the HL drift chamber is the possibility to implement a cluster counting technique. So when you have, let's say, if you are using a helium-based gas with a drift chamber, it's possible this. If you look at the signal, you can see that you can see the structure that are related to each single ionization cluster. And so you can, thinking about it, is possible having a right, let's say, acquisition system to identify the structure and count the cluster. So instead of making a charge integration. With this thing, so if you make some extrapolations and calculations, you can think that using the cluster counting, so counting class, you can reach a resolution on the particle ID that is better than, let's say, energy loss. I am going from 4% at a level of 2%. Let's just point out that with the cluster counting, you can think to improve the spatial resolution too, but it's not the aim of this, not the main topic of this for the DA chamber, DA drift chamber. So now, assuming that you can reach this better resolution on single, so on particle identification for single cell, now you can predict what you should expect on a particle ID of the entire chamber. And you can see on the plot on the top that, let's say, just stay concentrated on the blue curve, that is a pi kaon separation that is important in the content of FCC. You will have a better than 3 sigma separation over the entire range of the momentum respect of the Gieverde X that is not covered all the entire range. There is just a little tiny part that is missing, but you can think to recover with a different technique. Just take in mind that it's just analytic calculation on test beam results. Another point, the picture in the bottom left, just figure out which is the efficiency in the identifying counting the cluster you need for having, using efficiently this technique. You can see that 16%, so better than 14, but 16 and 18 efficiency, 18% efficiency is good enough to reach the goal. Just move on on what is the expected, let's say, performance on the entire detector. So to do that, we implemented a full simulation of the engine with the drift chamber plus the silicon detectors, or with the full tracking system. And after we make some, let's say, simple camel fitting of the track to reconstruction. And after to evaluate, let's say, the impact of the background, we started to implement the the tracking system inside the official FCC software, but this implementation is still ongoing. Now, what are the results with the full simulation study? So for the moment, for this study, we assume that we can reach a 100 micron resolution in average for the single drift shell, and this was confirmed by MEG in the published document of MEG. And for simplicity, we use that resolution for the silicon detector is used like, let's say, a digital device. So we are assuming just a pitch divided by square root of 12. And in this plot, you can see so the performance, how they go as function of the angle. And you can see that in the drift chamber, we have a lot of hits, more than 100 hits almost over the entire coverage. And we started to afford the pattern recognition and a tracking efficiency study. And we can see that we have a great efficiency over the whole momentum range. I say, why using a drift chamber and not, let's say, a full silicon detector approach, tracking approach? Is because since we are in a range of momentum up to 100, that we are far from, let's say, the asymptotic limit where the multiple scatter is not relevant, we are in a range of momentum where the multiple scatter is still has a relevant effect. So in this plot, you can see in a resolution sigma pt over pt square, a comparison between, let's say, CLD plot, that is another full D reconstructed proposed for FCC. The red curve is just making it almost similar, but with difference in layout, but almost equivalent full silicon experiment in our simulations just to be sure that there are no many bias between the two studies. And then the blue curve is what is should expect to obtain with the idea tracking system. So drift chambers in the central plus the silicon vert. You can see that you gain a lot over the whole over most of the momentum range, and you can reach ultimate resolution at the limit that is in the, let's say, goal, close to the goal of the FCC.
1 minute remaining.
Okay, I will try to speed up a little bit. So just to make more study, we using full simulation is not very convenient. So we just develop an analytic model to parameterize all the features of our combined detector. And let's say the red curve is comparison with let's say this model and the point are the full simulation. And after now making a change, assuming that you can use the silicon detector with better performance, let's say not using in a digital mode, but using clustering and so on, you can improve the resolution, let's say from in the 100 GP range from 4 less to 310 to the -5. What is the impact on the full measure? So using this fast simulation, we just try to study, see which is the impact of some of the important measures. You can see the blue curve that you are very close to the, let's say, ideal detector. So in the plot on the bottom, in the black curve is just what you expect if an infinite resolution detector. The black curve is what you have for the ideal detector. The red curve is for full silicon based. As I told, with we try to approach the problem of which is the heat occupancy and the background induced on the detector. In the FCC, most of the background coming from the gamma irradiated at the interaction point, but the preliminary studies show that this should be not an issue. The occupancy will in a well under control limit. Just an outlook on the R&D. So we are doing some proceeding R&D on the mechanic, on the mechanics aspect, R&D on using possible different, let's say, metallic alloy for the wire, or new technology, let's say carbon wire for the wiring. And you can see in the picture just at BMP Institute in West Bisque, they are developing a machine to make a coating, effective metallic coating on the carbon wire. And there is R&D on the cluster counting techniques, let's say electronic, to really implement the cluster counting in the R&D. So just let me go to the summary. You can read it, but just very briefly. So we have designed a detector, let's say a central detector and a full tracking system that could be could be working at the cost center of FCC. It is some special issue like very light and the possibility to have a good particle identification. That's it for my side. Thank you.
Thank you, Gianfranco. I don't see any hand raised, and taking into account the time, I propose we directly move on with Beatrice Mandelli on the performance studies of RPC detectors with environmentally operated with new environmentally friendly gas mixtures in the presence of the LHC-like radiation background. So we can see well your slides.
Okay.
And also hear you. So
yes. Great. So we start.
Exactly. Go ahead.
Yes, so in this talk I will give a brief overview of the studies that are ongoing nowadays to search for new environmental friendly gas mixture for the resistive plate chamber at the LHC experiment. After a brief introduction of why we're looking for alternative, we will see the characterization of this detector with different eco-friendly gas mixture, and then their operation at GIF++ with muon beam and in presence of a LHC-like gamma background radiation. So why we're looking for alternatives? Can you see my mouse?
Yes.
Okay, great.
Very well.
Yes, okay, so in this plot, you have the CERN greenhouse gas emission in run 2. And as you can see, the main contributors are the RPC detector that are used in the ALICE, ATLAS, and CMS experiment. Indeed, their gas mixture contain two greenhouse gases, the C2H2F4, also called R134A at 95%, and the SF6 at 0.3%. So, CERN is trying to reduce the greenhouse gas emission, and you can have more details on that in the talk of Roberto Guida of yesterday. Behind the fact that CERN is aiming to reduce this emission, there is also another point to take into account, that is the European Union regulation that started in 2015, that is aiming to limit the total amount of the most important gases that can be sold in Europe. Here, indeed, you have the hydrofluorocarbon phase down, of which the R134A is part. And as you can see, we will arrive at run 4 that in Europe, only 25% of the consumption with respect to 2014 can be sold. What does it mean that? It means that the availability of these gases are not known for the future and that the price are already increasing. So the reduction of the use of the freon is fundamental for the next LHC run. So what we can have as alternative? Industry already started to look for alternative. And indeed, there are these new eco-friendly that are liquid or gases that have been developed for refrigerant and as high voltage insulating medium. And the operation for the RPC is not straightforward. Let's take some example. For the R134A, that is the main contributor. Now in industry, we have available this hydrofluorolefine that have a molecule that is very similar to the one of the R134A with 1 carbon more, basically, as you can see here, and have a very, very low global warming potential. For the SF6, they start to have alternative basically in the last few years, and the most using one are these Novak from the 3M company that you see they have a very complex chemical formula but very low global warming potential with respect to SF6. The goal of our R&D is actually to find an eco-friendly gas mixture that is compatible with the current ATLAS and CMS RPC system. And this is very important because you will see that it's very difficult because we cannot change in the experiment high voltage cable, front-end electronics, and all the infrastructure that is around. So, first of all, is characterization of this gas mixture in the lab. Here you have the setup, where you can see that we have a gas mixing unit that can mix up to 6 different gases. We have several gas analysis tools. We have obviously RPC that are like the one that we have installed in ATLAS and CMS, so high pressure laminate with a 2 mm gas gap. And we basically record the signal with a kind digitizer that is basically allowing us to record all the interesting parameters that we need for characterization, pulse charge, pulse rate, time, and so on. If we look at some results, the first thing that we tried to do was to directly replace the freon with the HFO. But this actually doesn't work for two reasons. First of all, the avalanche signal is much smaller with HFO gas mixture. And the second point is that we need a very high voltage, more than 12 kilovolt, to start to see some signals. And nowadays, the detector are working the experiment at about 9.5, 10 kilovolt. So it's much higher. So the first things to do is actually to try to reduce the voltage working point. And to do that, you can work on the gas pressure by reducing the mixture densities. This can be done by adding an inert gas. The first trial was the helium that in a first approximation doesn't take part in the formation of the signal. So what we did was to try different concentration of helium. And once we saw that even with different concentration of helium and HFO in the gas mixture, we didn't have good results, we arrived to a gas mixture made of 5 components. So we still have the SF6 and the isobutane. We add helium to lower the voltage working point, and then we have half and half of the R134A and HFO. With this gas mixture, we arrived to a global warming potential of 800 instead of the 1500 of the standard gas mixture. Here you have an example of performance. So in black, you have the standard gas mixture. Continuous line is the efficiency, and dotted line are the streamer probability. If we take, for example, the red curve with this mixture containing 20% of helium and half Freon and R13 and HFO, you can see that the voltage working point is still higher, but acceptable. And the streamer probability is very similar of the one of the standard gas mixture. So this gas mixture actually is working pretty well. At the time of the test, we actually then discarded this gas mixture because helium it was not possible to use helium in the experiment. So we moved to another gas, and we tried the CO2. With the CO2, 10% of CO2 is lowering the voltage of 800 volt, more or less. The problem with CO2 is that it's taking part in the formation of the signal, and then it's more difficult to find a good gas mixture. So there are two different things that we did. Again, a gas mixture, we started with a gas mixture containing half CF4, half Freon and half HFO with the addition then of CO2. And you can see basically that by increasing the CO2 concentration, we are decreasing the voltage working point. But if you look, for example, at the pink curve, okay, that are with 50% CO2, you can see that we have a very high streamer probability. So what we did, we worked with the SF6. So we added a bit of SF6, and you can see with by increasing the SF6, we have a streamer probability that is quite good. It's more or less 2 times the one of the standard gas mixture that is here in black. Okay. The point is that by adding SF6, we are increasing the global warming potential. So we pass it from 400 to 500, 600, but still a factor 3 with respect to the standard gas mixture. In the last year, we also started to look for a replacement for the SF6, as basically this new Novec came out in the market more or less 1 year ago. Indeed, in the SF6, you use it a very small quantity in the RPC gas mixture because it's only 0.3%, but it contributes for the 5% in the global warming potential, because remember the global warming potential is about 24,000. I will not go into the detail of all these tests, but I will show just you a few examples. Again, we have in black the standard gas mixture, and if we take this Novec 4710, what we did from the standard gas mixture, we take out the SF6 and we added the Novec in a concentration of 0.1%, and you see basically that the performance are exactly the same in terms of efficiency and in terms of streamer probability that is over there. So this Novec is very, very good as a replacement for the SF6, but there is a problem because we figure out that this gas may react with water. And remember that in the RPC gas mixture, we have 40% relative humidity. So now studies are ongoing to try to understand if there can be any problem in having the water with this Novec for the performance of the detector. We tested also other novel gases or other type of gases. Performance are all the time pretty good, but there is always a problem that can be a bit higher streamer probability, or if we take, for example, the case of the CF3I is toxic and mutagenic, so it cannot be used in the experiment. So this R&D part of the SF6 is just started, and we are still working on that. If we move now to the test of the detector in LHC like background radiation, so we move it to the GIF. And at GIF, we had, during test beam period, we have a muon beam of 100 JV, and there is a cesium gamma source of 14 terabecquerel. Here you have a picture of the setup with the detector over there. Okay, and here you have the source. Basically, what we did, we selected two eco-friendly gas mixture that have pretty good performance with respect to the standard CMS and ATLAS gas mixture, and we perform our test. So the gas mixture that we selected are the two that you can see over there. And you see we have one with 40 and one with 50% of CO2. And we have a mix of R134A and HF4 in the same proportion. Isobutane again and SF6. Okay, so we tested the detector at different gamma rate. And here you have the results at 40 kilos per centimeter square. In blue, you have the standard gas mixture, and in orange, the one with 50% CO2, and in green, the one with 40. As you can see, we have basically the test beam measurement confirm the laboratory test, because we have more or less the same high voltage shift with operating with HFO gas mixture. And the streamer probability is about a factor 2 higher with HFO gas mixture. The problem that we figure out are about the detector current that are pretty high, a factor 2 more with this eco-friendly gas mixture. And this could have affect aging problem for the future. So long-term tests have to be done. If we look now at the 40% HFO gas mixture, here you have a plot again on the efficiency and streamer probability with different gamma rate. And you can see that the efficiency does not depend on the background radiation for all the absorption factor. And the streamer probability decreases with the increase of the background radiation, as it is for the standard gas mixture. And this is due to space charge effects. We also did several studies on the pulse charge, both for avalanche and streamer. And here you have an example with source off, so basically cosmics, and here at 40 kilos per centimeter square. What one can see is that while the avalanche pulse charge is the same in the two cases for the standard gas mixture, is decreasing in the case of this eco-friendly gas mixture. The same happens for the streamer probability, that is decreasing with the increase of the radiation. And this again is due to charge development effects inside the detector. Last but not the least, we are also looking at creation of the impurity. Indeed, it's very well known that the R134A breaks under the effects of the high radiation and electric fields. It breaks, creating several molecular, as you can see here, several impurities, and most important is also creating fluoride radicals that are very chemical reactive and can damage the surface of the detector. These fluoride radicals were also seen during LHC run 2 in the RPC installed in the 3 experiment. So what we did was to do some tests in order to understand if also the HFO breaks and how much. Here you have a plot of the fluoride concentration as a function of the gamma rate. In black, again, the standard gas mixture, and you can see the production of fluoride increase with the increase of the gamma rate. If we look at the gas mixture containing 40% CO2 and 30% of HFO, we can see that the production of fluoride is 4 times higher. We then
Can you soon come to the end of the presentation?
Yes. So what we conclude there is the fact that if the HFO breaks 10 times more easily than the freon, and this could have effect on the long-term operation of the detector. So if we look at the conclusion, our R&D goal is basically to find a gas mixture, eco-friendly gas mixture that is compatible with the ATLAS and CMS RPC system. And so we have seen that basically the eco-friendly gases that are available on the market are doesn't work very well if the substitute is direct in the gas mixture. Our project is divided into two main phases. The first one is the characterization of RPC with different eco-friendly mixture, where we mix from 4 to 6 components, and this is still ongoing. And once we find a good candidate that shows similar property with respect to the standard gas mixture, we move to the GIF in order to study the detector performance under high background radiation, and especially see if there are any long-term effects in terms of aging for the operation of this detector. Thanks.
Thanks. Is there any quick question? Then I ask everybody not presenting to mute. Thank you, Beatrice. Also, I encourage everybody to stay until the end of the session because we want to take a virtual session photo. So now we continue with Mattia Soldani. Thanks for already sharing. And he will present on next generation ultra compact calorimeters based on oriented crystals. We can see you and the slides very well.
Yeah, very well.
Yeah, also hear you. Go ahead.
Okay, fantastic. Okay, so let me start by saying that I speak on behalf of the Elliott experiment, which is devoted to the study of the interaction between high energy particles and the oriental lattice of crystalline media. Therefore, today I will present a novel idea that exploits the crystalline nature of the most common media currently used in high energy physics calorimetry. Of course, a quick summary of the coherent effects that occur in oriented crystals will be given, as well as a discussion on the status of the investigation and on the possible applications of this concept. So when a charged particle crosses a crystal with small angle with respect to the lattice axis, that is the periodic arrays of nuclei, the electromagnetic potential it experiences is not Coulomb-like, but rather can be described as a continuous barrier. This forces the particle to an oscillatory motion with subsequent emission of peculiar electromagnetic radiation. In particular, above few GeV in input, the interaction features an intense radiation emission, which is peaked at high energy. Now, let's explore the most extreme case with some quantitative coordinates. Let's consider a particle whose input angle is within this value here and whose energy is so that the Lorentz boosted lattice field is about greater than the Schwinger QED critical field, this value here, which equals to require that this quantity defined here, this key, is greater than 1, which occurs at about 10 GeV. So in this particular regime, the so-called strong field is attained. And as a consequence, there is an important enhancement in the radiation intensity and energy. This can be seen as a consequence of the fact that the overall field experienced by the projectile within the so-called radiation formation length, depicted here, is much higher. And interestingly enough, the per production by high energy photons is affected by the strong field in the same way, therefore gaining a higher cross section. As a consequence, the electromagnetic shower, that is the successive occurrence of Bremsstrahlung and per production starting from a single input event, develops much faster, which corresponds to a strong decrease of the effective radiation length of the crossed crystal. Of course, this can result in a measured improvement in calorimetry, in which one needs a detector that forces the input particle to start a shower and is able to fully contain it, of course, generating a signal which is proportional to the input particle energy. Well, such lattice effect can be exploited to develop high compactness and budget-friendly detectors with the same light yield as the current state of the art. And of course, I think this drawing here is quite self-explanatory. Now let's turn to what has been done recently on this topic by my team. Well, we mainly focused on the study of lead tongue state, or PWO, which is quite commonly used in HEP calorimetry, with the outstanding example of the CMS incl, thanks to which its scintillating and mechanical properties are well known. In particular, in spite of quite a low light yield, PWO features high Z, high density, general good production quality, and is also quite cheap. Also, from the lattice point of view, both its principal axes, depicted here as 001 and 100, have quite high electromagnetic potentials and are therefore suitable for the strong field regime. Well, we performed several beam tests with electrons and various PWO samples in both the strong field regime, which was done at the CERN North area with 120 GeV beams, and also the sub-strong field regime, which is attained when K is between about 0.1 and 1, which was done at the DESI beam test facility. In particular, we tested these two samples. First, a thin strip with a thickness of 20 to 30% of a radiation length along the principal axis was tested at CERN, where radiation length in thickness along the 100 axis was tested at DESI. So the first thing we can show is that the energy loss inside the crystal, depicted in this plot here, has a spectrum that matches the one obtained from the simulations in both the axial alignment and the random condition, that is the amorphous-like orientation of the sample, very far from the axis. The comparison with simulation depicted here allowed us to determine a 5-fold reduction of the radiation length when on axis, which is, of course, quite remarkable. Of course, the angular range of the strong field effect was then also explored, and one can see here in the bottom left that the effect peak, which is here, extends up to more than 2 milliradians. However, it was also observed that the axis affects the interactions in some way up to about 1 degree, as expected by the strong field regime effects. In 2019, we also perfected the way to read the PWO scintillation light out, which was done via a silicon photomultiplier coupled to one of the strip sides, as you can see in this picture here. Again, there is good agreement between the light output spectra obtained from the data, shown here, and the simulation. Then we had a beam test at DESI, and the DESI 5.6 GeV electron beam line allowed us to explore the already mentioned sub-strong field regime. Of course, this analysis work is still in progress, but one can already see here that the energy loss spectrum modifications with respect to the amorphous-like conditions are macroscopic and have wide angular range. We talk about again, 1 degree. Okay, so let me now spend a few words on the various applications this concept might successfully be exploited for. The idea of a compact electromagnetic calorimeter is interesting in the development of a fixed target experiment, in which there is in general need for quite a small transverse coverage. Of course, the compactness is an absolute upside, but however, one may also think about a trade-off between compactness, cost, and mechanical precision. In this scenario, depicted here in this drawing, only the upstream layers of a segmented homogeneous calorimeter would be made of oriented crystals, leaving the rear part in random configuration. Also, it is quite interesting to add that, as shown in this simulation results, when on axis, the shower longitudinal peak is indeed located quite upstream inside the detector. And most importantly, its position is independent on the input energy, which again is particularly interesting, especially considering future experiments that explore the TeV scale. Well, incidentally, this concept is already under study for a specific application, that is the small angle calorimeter of the Clever experiment, which is going to study the K-long decay, the rare K-long decays at the CERN SPS. Okay, this detector would be located in the downstream part of the Clever apparatus, right along the path of the neutral hadron beam, which is why we're actually opting for oriented crystals. Indeed, oriented crystals would meet the need for a device with radiation length as short as possible and with nuclear interaction length as high as possible at the same time, in order to be able to detect small angle photons with high efficiency while being mostly insensitive to neutral hadrons. And this is possible because the nuclear interaction length is unaffected by the lattice orientation. Speaking of the materials, lead tungstate is a suitable candidate for the development of this device, but also lead fluoride, which is a fast Cherenkov-emitter crystalline medium. Of course, another intriguing possibility would be to exploit aligned crystalline layers as sampling calorimeter passive media. Clearly, this configuration would come with many advantages. Of course, all the ones I already described in the previous slides, but another outstanding one being the fact that no modifications would be made to the current state of the art in terms of the active layers and the readout, which are both well-known technologies. Actually, we already tested crystalline tungsten with both electron and photon beams, seeking an upstream photon converter candidate for Clever. And there we observed the pair production enhancement in the strong field regime, as you can see in this plot, showing such enhancement as a function of the tagged photon energy and of the input angle. Indeed, one can also think about a compact gamma calorimeter for a satellite board observer. It is needless to say that the reduced weight and size would represent in this case a major absolute upside for a satellite payload. Also, it is possible with the current pointing technology to aim at a point like source with the angular precision required to exploit the strong field enhancement, while it is also worth mentioning that oriented metallic layers could be exploited to make the gamma converters, that is the upstream part of the detector prior to the calorimeter, much thinner, thus further reducing the overall setup material budget and the moldable scattering contribution, with a major benefit by devices of the same kind as, for example, the Fermi LAT, which is depicted in this scheme here.
1 minute. Yeah.
Okay, thank you very much. I just got to the conclusion, and let me just say that we at the Elliott experiment hope this concept might get to represent an important milestone in electromagnetic calorimetry. Speaking of the future, given the fact that we are facing a newborn research topic, we have quite a lot of ideas and plans, which include, of course, testing new crystalline materials, such as lead fluoride and iridium, and most importantly, developing a custom readout system for the sample optical light output. This is particularly important to us because asymptotically, we would like to apply this scheme to a large-scale calorimeter prototype. So thank you very much, and I will be glad to answer your questions now.
Thank you, Mattia, very much for the clear talk. So are there questions? We still have a moment for some. So for beam tests, which location do you go to?
Okay, for the time being, we exploited the high energy beam lines of the CERN North area, while we explored at a lower energy scale we exploited the DESY T21 experimental facility.
And this is also for the future, for
of course, we have already a beam test planned for this December, again at DESY. Of course, this is coronavirus dependent, but at the same time, we would like to enlarge our experience, maybe by also considering the possibility of using the CERN East Hall lower energy beam test facility. Of course, again, further beam tests at third north area are sub judice, and we hope we will be able to get there in 2021 or 2022 to go on with our study in the strong field regime.
Thanks. Then I would like to thank you for the presentation again, and we move on. Brennan Hackett are you connected by now? I have not seen you, nor any slides are uploaded. This is why then I propose we skip this talk, and Brian, you will be the next one on low radioactivity argon for dark matter and rare event searches. I hope this is fine to jump directly to you.
All right.
I can already hear you, and you start this sharing.
All right, can you see my slides?
Yeah, and perfect in full screen, so please go ahead.
Okay, good afternoon or good morning, wherever in the world you may be. My name is Brianne Hackett. I'm a postdoctoral researcher at Pacific Northwest National Laboratory. Today I'll be talking to you about low radioactivity argon for dark matter and rare event searches. In particular, I'm going to be focusing on the low radioactivity argon aspect. Okay, so DarkSide 50 was the first dark matter detector to use argon for a dark matter search. It is located in Grenzhausen National Laboratory. It's a dual-phase liquid argon time projection chamber contained within a liquid scintillator VITO, which is then contained within a water Cherenkov detector. So on the right here, you see the top picture is our liquid scintillator VITO before it was filled with the liquid scintillator. So you have a nice image here of the cryostat in the center with all the PMTs in the scintillator VITO. And then the bottom picture here is a picture of the water Cherenkov detector. Again, before it was filled with water. And so in the center here, you can see this is the neutron VITO, the liquid scintillator VITO. And covered in Tyvect to help promote light. The TPC for DarkSide 50 was filled with 50 kilograms of argon. The first fill was in 2013. It was filled with atmospheric argon. And then in 2015, it was emptied and then filled again with argon sourced from underground. Now, the argon from atmosphere contains argon-39 with an activity of 1 becquerel per kilogram. This represents a large background for dark matter searches. So when DarkSide filled with underground argon, we measured an activity of argon-39 of 0.73 millibecquerel per kilogram. So by using underground argon, we were able to reduce the argon-39 background content by a factor of about 1,400. Any residual argon-39 that was in DarkSide 50 is likely from an air infiltration that happened during the extraction of the argon-39. On the global scale, and for any future experiments, argon, so DarkSide 20K and Argo, they will be using argon sourced from underground. And then these are a couple other experiments that would benefit from using argon sourced from underground as it's low in argon-39 content. But these experiments require massive amounts of underground argon. So in particular, the next generation in the DarkSide program is DarkSide 20K. It will also be located at Grenzhausen National Laboratory. It is again a dual phase liquid argon time projection chamber. It will require 50 tons of our underground argon. So underground argon, it's in the atmosphere. Argon-39 is produced from cosmic ray interactions, primarily from argon-40. As I mentioned earlier, it has an activity of 1 becquerel per kilogram, which represents a large background for dark matter experiments. So in the atmosphere, you have all these different production mechanisms for argon-39. But if you want to use argon for dark matter detection, then you need to find a way to get rid of this argon-39 content. And so what you can do is you can look for sources that are low in argon-39. So then if you look to argon that is underground, then the actual production mechanism for argon-39 is different from what you find in the atmosphere. So underground, the argon-39 is produced from potassium-39 and its interaction with neutrons. These neutrons, if you trace them back, they come from the radioactive, from the radioactive decay of uranium and thorium. So if you can find a source underground that is low in uranium and thorium, and ideally also low in potassium-39, then you have the potential for finding argon that is very low in argon-39 content. So to that end, a search was undertaken in 2009 to find a source of underground argon. And they did that in 2009. And so that source is from a CO2 well in Southwest Colorado. In particular, it's in the McElmo Dome area of Doe Canyon in Southwest Colorado. This CO2 well had 440 parts per million argon within the CO2 stream. This site in Colorado is currently the only known proven source for argon that is low in argon-39. This poses the question of where else in the world can we find argon low in argon-39, which is an ongoing effort for future dark matter experiments which intend to use argon as a target. So for DarkSide 50, the underground argon was extracted at a plant here in Colorado. Then it was shipped to Fermilab for purification. And the underground argon production averaged 140 grams per day in order to fill the 50 kilogram DarkSide 50 target. The DarkSide 20K and any future planned argon experiments will need much more underground argon, and the underground argon will need to be produced, purified at a much faster rate than was done for the argon for DarkSide 50. So in order to get argon sourced from underground to DarkSide 50, what needs to happen are 3 basic steps, really. You have to extract the argon from the CO2 wells with a designated plant. This plant, which is in preparation right now, is called Uranium. This plant will be located next to the site of the previous underground argon extraction. The next step is to ship this underground argon by ship from Colorado in the US all the way to Sardinia, Italy for a chemical purification. And this chemical purification is going to happen at a plant called ARIA. And then the next step is the underground argon will be shipped again by ship, by sea, to LNGS for insertion into DarkSide 20K. along the way, we would like to have a quality assurance. So a small portion of the underground argon is going to be sent to DART for argon 39 measurement. So again, one can ask, since the underground argon is going to be shipped by sea, what happens if we decide to fly the small portion of the underground argon to DART instead of shipping it by sea? So what is the ingrowth of argon 39 during its flight, which is another effort that is ongoing here at PNNL. So, uranium. It's going to be located next to the previous location that the dark side 50 underground argon extraction occurred in Colorado. We're going to extract the underground argon from the same source as the dark side 50 target. This extraction and the chemical purification plant is going to be built by Polaris, an Italian company. The argon is going to be extracted at a rate of 300 kilograms per day, as compared to previously with dark side 50, they only averaged 140 grams per day. And this underground argon will have a purity of 99.99%. So here at the bottom is a little schematic from Polaris of what the plant is going to look like. So in the first phase, first part of the plant, they're going to do a first carbon dioxide separation, and then it will undergo a second carbon dioxide separation. And then we'll have the first argon purification, and then it will undergo a second argon purification in order to reach our 99.99% purity. So here, this is the future site of uranium. So right now it is an empty field. Off to the left is the previous site of the underground argon extraction. So we'll just be building our plant here in this field to extract and purify the argon.
1 minute is left.
Okay, thank you. The next step is ARIA. So ARIA will be a cryogenic isotopic distillation plant. It's being installed in a mine shaft in Sardinia. It'll be one of the tallest, if not the tallest, distillation columns built. And ARIA is designed to reduce the argon 39 isotopic fraction in underground argon by a factor of 10 per pass, and its production rate will be several kilograms per day. But for dark side 20K, at the time scale needed for dark side 20K, ARIA will only be able to provide a chemical purification. So the underground argon is just going to undergo, it's just going to be put into the distillation column to separate out any impurities left over. And using ARIA for chemical purification, we'll be able to produce argon that is ready for dark side 20K at a rate of 1,000 kilograms per day. The last step for quality assurance is for the underground argon, a small portion of it, to be shipped to DART, which is located at Canfranc in Spain. DART is going to be housed within the RDM experiment. It is a small single-phase liquid argon detector with an active volume of about 1 liter. And it's going to be able to measure an argon 39 depletion factor on the order of 1,000 with 10% precision. And it'll be able to measure the argon 39 content, not only for dark side 20K, but any future argon experiments that come along. So thank you.
Thank you very much. Is there any question? Can you comment on how long it took to find this specific location? And was there many then measurement steps in between, or how is it done?
So I'm not entirely sure of the exact timeline for how long it took them to find the source. I think it was somewhere on the order of 1 to 2 years, maybe longer. But I do know that the three men that I showed in the picture got in a car together and drove around the Colorado area where there are multiple CO2 wells, and they sampled from many different wells, and before they found the one well, which is shown in the picture here, that had argon in the well that they could actually measure. So they were taking samples from each wells and measuring them in the back of their car.
And is the search for new wells still ongoing, or is for the moment then the community fine with this new well on the amount which is delivered?
For the moment, the well that we're using in Colorado is fine. There have been efforts by myself and by others to search for other sources. Those are still ongoing as far as I'm aware.
Thanks a lot. Then I would also like to thank you, Brian. I would like to thank all speakers since we come to the end of the presentations. Just before disconnecting, I ask everybody to just switch on the video and we take a virtual session photo. And of course, it's your own decision if you switch on the video. We will then post it also in the Mattermost chat, and just that you know. Let me see, I think we can do like this. Maybe a few more. So we wait for a moment. Yeah, very nice. Okay, anybody else? Okay, very nice. Good, then I take the picture. Let me see here. Good. So thank you, everybody. Thanks for the questions. And then I hope you enjoy further the virtual conference, and we close the session. Bye.
Thank you. Bye.
Thank you, everybody. Goodbye.
Bye.
Bye, everyone.